All right. Let's try that again. All right, let's do our sound check. Do I hear myself? I do hear myself there. Okay, now let's do camera check. Do I see everything showing up from the camera? Do I see my hand moving? Yes, it looks like it's working. Okay, then we are good to go. Apologies in advance. I have a little bit of a case of the sniffles today, so I hope that doesn't bother people too much. I think the show must go on, so I'm not taking the day off. I started a little bit late into the school year, and I've got some catch-up work to do. So, yeah, postponing is not something I want to do until I've at least caught up with most people's AP Physics classes. So, what is the agenda for today? Today, the plan is to take care of a problem that I left you guys with at the end of the previous stream. Well, the physics part of it anyway. And also, we need to go back and, after doing some work on my own time, I found, where was it? Was it in here? Somewhere here. I did an example where, oh yeah, here it is, found it. Yeah, I messed this up, an alternative derivation of the second equation of kinematics in the case where the acceleration is negative and your velocity starts off positive but goes into the negative. And of course I could do the reverse of that situation where you start with a negative velocity with a positive acceleration upwards, and also the reverse of the original situation where we started off with a positive initial velocity and it only increased from there with a positive acceleration. We could do the reverse of that. We could just do this flipped over. But both of those flipped over versions are basically going to be the same proof. So I only need to prove this second scenario just to not have it living rent-free in some people's heads if they're still bothered by it. So yeah. We're going to attempt this alternative proof again. I figured out what I did wrong last time, and I will make the necessary corrections this time around. And after we're done with that, the plan will be to introduce the topic of free fall. Basically, we're just going to do kinematics in the vertical direction. How does kinematics work when gravity is involved? And after that, we will look at some example problems if we have the time for them. And depending on how far we get into those problems, if we get into them at all, we might just move on to the next unit next time, or probably what I will do next time, most likely, is just do kind of mixed horizontal and vertical problems. Just do some like advanced problems from the current unit before moving on to the topic of projectile motion. So yeah, that is the agenda for today. So let's start off with this problem. Let me actually open the book and reread the problem statement. Oh, and let me unplug this headset. There we go. I knew there was something that felt wrong. And I live in my head way too much if I don't even notice the headphones on my own head. Okay. Open book. And find the cable car problem. Here we go. It says, a certain cable car in San Francisco can stop in 10 seconds when traveling at maximum speed. On one occasion, the driver sees a dog a distance d meters in front of the car and slams on the brakes instantly. The car reaches the dog 8 seconds later, and the dog jumps off the track just in time. If the car travels 4 meters beyond the position of the dog before coming to a stop, how far was the car from the dog? And there's a hint that says you will need 3 equations. So let's go ahead and figure out how we want to do this problem. I've done it numerous times with many students. This is one of my favorite problems to give students because of the challenge it provides. So let's see. I might screw up part of this, but I think that's still valuable stuff to see anyway. Because what's more important than answering the problem itself is really just learning the problem-solving strategy for something like this. There's a number of things that can trip students up with this problem, and I think really digging into, the thought process for this problem is the most important part for those students. So let's see what I can write. So I know my equations of kinematics. I have some of them already up there. Let me write them over here. So we had V final, not literally final, V next is probably the better way to think about it, equals V previous, or what I usually call V initial, plus acceleration times time is our first equation. Our second is displacement equals starting speed, or starting velocity times time, plus 1/2 acceleration times time squared. And V final squared equals V initial squared plus 2a delta x. So those are 3 equations that we have, and we don't necessarily need to use all 3 of these. When the hint says we need 3 equations, it doesn't necessarily mean that we use all 3 of these, because we've got different starting and stopping points for which we can write equations. So, for example, I can write an equation from this starting point when the driver first starts hitting the brakes to when they finally stop. I could write an equation for that, and I could do, let's see, we have some unknown Vmax, an unknown constant Vmax, whatever it is, it's some sort of constant value. It's not a variable, despite the fact that it's unknown. And we know that it's going to come to a stop, so we know V final is 0, and we know the time is going to be 10 seconds. And we don't really know what the acceleration is, but whatever the acceleration is, it's going to be the same for this interval over here and this interval over here. So if we use the first equation, we can get at least an expression having to do with the acceleration. We can at least define our acceleration in terms of our unknown starting speed. So let's go ahead and do that. I'm going to write, so the final, that is the 0, is equal to our starting velocity is Vmax, plus the acceleration, we don't know what it is yet, times 10 seconds. And from this, we can rearrange it. We can subtract 10a on both sides and divide by -10, and that gets us acceleration equals negative Vmax over 10. Might be useful, might not be, but we'll see. Okay, so that's one equation that might prove to be useful. We also are trying to figure out what this distance d is. So, fortunately, I don't need to know how fast I am moving over here. Fortunately, I don't need to know that. I guess I would call it v dog if I had to give it a name, because it's the speed It's the velocity you would have once you reach the dog. So I could write an equation having to do with this. I could actually use the first equation again, except instead of doing it from here to here, I do it from here to here. But that introduces a new variable, and sometimes you do need to introduce new variables in order to solve a problem, but oftentimes introducing more unknowns to your problem makes it worse. So this is probably the first pitfall that students might end up tripping in. I'll go ahead and write it anyway. We can say, what do I want to do? I guess, yeah, I'll use first equation again. I can say v dog equals v max plus the acceleration times 8. And I suppose you could plug in negative v max over 10 in for the acceleration now, and get this to be, let's see, that would become negative 8 over 10 v max, so negative 8/10, negative 0.8 v max. So that would give us v dog, velocity when reaching the dog is equal to v max minus 0.8 v max equals 0.2 v max. Well, at least now we've saved it somewhat, because even though we introduced a new variable, we've found a way to express it in terms of an unknown that we already had. So we're back to the same original number of unknowns, but you don't really need to do this. It turns out that we don't actually need this step, but that is one of the common missteps that you could take. And yeah, the hint to avoid doing this is you're introducing a new unknown to the problem that you probably don't need. We already have what even are our unknowns. Our unknowns are Vmax and acceleration and d, right? We start off with those three things being unknown. We start off with three unknowns, which means we need three equations, but once you introduce a fourth unknown, you're going to need a fourth equation. So this, I guess, was that fourth equation to deal with the fourth unknown we introduced. It's an unnecessary step, and with time and practice, you will start to recognize these. You will start to recognize, like, you won't know for sure until you work out the problem, but you'll start to develop a sort of sense of direction, a sort of hunch that this might be leading to a dead end. Maybe try this later if nothing else works. You'll start to develop that if you practice enough problems. Anyway, I want to write a displacement equation now, because with displacement, I only need to know the initial speed, which I already, well, I don't know it, but it's Vmax. Yeah, let's go ahead and write delta x, which from here to here is just going to be d. I guess I'll just call it d. D is equal to, let's see, v initial, which in this case is Vmax, times t, which in this case is 8 seconds, plus 1/2 times the acceleration. We could express it as negative Vmax over 10, but for now I'll just keep it as a, and then 8 squared. Okay, and that's a second equation, assuming this to be my first. And for a third equation, do I want to use the third equation of kinematics here? Well, if I were to do that, it does involve d. I could do, I guess it would be v dog squared equals v max squared plus 2 times the acceleration times d. But again, that refers to v dog, which is introducing a new unknown, which we probably don't need. So let's avoid that step and see what else we can do. How about we do another use of the second kinematics equation, and this time do it over the whole entire trip of the cable car. So delta x in this case would be d plus 4. So I'm going to do d plus 4 equals, and in this case the time is going to be 10 seconds, so it's going to be Vmax times 10 seconds plus 1/2 a times 10 squared. Oh, this is a nice pair of equations to work with because my three unknowns are just the same unknowns that I started with. I don't have to use any new unknowns. And I can immediately see I can eliminate one of my unknowns. I can eliminate d. If I just take this d plus 4 equation and subtract the equation above it, I can get rid of d, and now I'm left with a two unknowns equation. I'm left with an equation that has two unknowns, and better yet, my very first equation over here has those same two unknowns, which means I'll end up with two equations in the same two unknowns. I can solve those. So that's kind of the thought process. That's kind of how you can tell when you're heading in the right direction. And I don't expect you to just kind of develop this skill after seeing this one example. Like I said earlier, it takes a bit of experience. You practice problems of this kind of level of difficulty, and over time you just kind of gain a sense for it. So let's do bottom equation minus top equation. So d plus 4 minus d is going to be equal to 4 equals 10 Vmax minus 8 Vmax is going to be 2 Vmax. And then, let's see, 1/2 of 10 squared, half of 100 is 50. And then half of 8 squared is 64, half of 64 is 32. Half of 100, so 50 minus 32, that would be 18a. So I'd be left with 50a minus 32a equals 18a. And now that's my equation in two unknowns. Combine it together with this, or preferably, since I already went to the trouble of rearranging it, substitute acceleration with negative Vmax over 10. And if I do that, I'm left with 4 equals 2 Vmax plus 18 times negative Vmax over 10. And let's see, negative 18 over 10 is negative 1.8. So I'd have 2 minus 1.8 is 0.2. I'd be left with 4 is equal to 0.2 of Vmax. And if 4 is equal to 0.2 of Vmax, I might as well utilize that last bit of space I have over to the left. Now let's do this one in orange. I noticed while reviewing the videos that orange tends to show up better towards the bottom of the page for some reason, probably the angle of the lighting or something like that. So I'm going to try and avoid using this color closer to the top. Where was I? Right, 4 equals 0.2 Vmax. Whoops. What did I do? 4 equals 0.2 of Vmax. Divide by 0.2. 4 over 0.2 is 40 over 2 is 20. 4 over 0.2 equals 40 over 2 equals 20 equals Vmax. Okay, so that gives us the value of Vmax, 20 meters per second. I guess I will list it up here, or down here rather. Vmax equals 20 meters per second. What was the question asking for, though? The question was asking how far was the car from the dog, right? So what we actually want to solve for is the value of d. Let's see how we can go about that. I guess I would want to solve for the acceleration next. So acceleration equals negative Vmax over 10. Negative 20 over 10 is just negative 2. So my acceleration is negative 2 meters per second, also known as meters per second squared. And that allows us to solve for d using either one of these. I would rather use this one because I don't have to subtract a 4 at the end. It's just one less step. So 20 times 8 would be 160. And then half of negative 2 is just negative 1. Hold on, let me write this down. So d equals, is that visible on the screen? Yeah. Gotta make sure that my paper stays within the camera's view. D equals 20 times 8 plus 1/2 of negative 2, that's minus 1 times 8 squared. So that's 160 minus 64. 160 minus 64, subtract 60, and that's 100. Subtract 4 more, and that's 96. So d is equal to 96 meters, which means this full distance, the full braking distance of the cable car, is exactly 100 meters. How about that? Okay, that takes care of the dog and cable car problem. Now let's move on to that alternative derivation of the second kinematics equation. Yeah, this over here. Okay, so let's see. Do I want to reuse this drawing, or should I draw something else? I'll just reuse this one. Okay, so what I did wrong last time was, what did I even do? Let me see what my math says. So my math says, you know what? I don't even want to try and figure out what past me was thinking over here. Let's just go over what I should have done and leave it at that. So over here, this first orange triangle is above my horizontal axis. It's above my time axis. This represents a positive displacement. The area within this triangle is a positive displacement. The area within this second orange triangle represents a negative displacement. After all, when you try to calculate this area, if you were to calculate it as a triangle, you would have the base is just some amount of time, which should be positive, while the height is based on the final velocity, which should be negative. So it would make sense if you multiply a negative velocity by a base that's in positive time units, you should get negative displacement units. So what I should have done is I should have taken the area of this first triangle minus the area of this second triangle and left it at that. Displacement equals a positive triangle minus the area of the negative triangle. That's what I should have done. Now, defining those areas can be a bit of a challenge. I still want this concept of T star, this time when the switch happens between positive and negative velocity. I still want to have that. But maybe, you know what? Yeah, I'm going to redraw because I don't think this initial drawing is big enough for me to write all the stuff that I want to write down. Let's go ahead and actually redraw it. Where's my ruler? There it is. Okay. Probably not going to be the exact same diagram, but that's okay. Is that about halfway through? Looks like it. Maybe a little less. Okay, and then let's draw maybe something like this. Okay, hopefully that's asymmetrical enough. Yeah, it looks asymmetrical to me. I mean, it would still work if it was symmetrical, but we don't want to assume symmetry. That would be creating another special case, and we're looking for a more general proof. So yeah, this triangle does look a little bit bigger than this one, so it doesn't matter which one is bigger as long as one of them is. We have a V initial over here, whatever it may be, some positive value. We have, let me get the ruler again. We have a V final over here, some negative value. That's going to be our time axis, that's going to be our velocity axis. And we've got two areas to work with. And then there's a time over here where the velocity reaches 0. I'm going to call that t star. And then I'm going to call the full time, the total time for this whole change to occur, I'm going to call that, oops, not orange. I said I wasn't going to use orange towards the top of the page. I want to take this whole interval, I'm going to call that my total time, which I guess I should have called t total from the outset, but we'll just call it t here. Okay, that would mean, since I'm trying to calculate the areas of these two triangles, I need to define their bases and heights. So the base of this triangle, it starts from time 0 to time t star, so this is just t star seconds wide. I know seconds aren't really a unit of width, but in this graph, they can be interpreted as such. So that's just going to be a width of t star. This is going to be what's left out of the total time. So the total time is this big T, and we know this much of it is t star, which means this must be t minus t star, the full time minus the time to reach 0 velocity. And now I want to come up with, do I even have room for it in here? Yeah, just barely slipped it in. I want the height of that triangle to be, let's see, it's the distance between v initial and a velocity of 0. So if I define it as the second velocity minus the first, that would be 0 minus v initial, or negative v initial. And then for this height, I might actually want to revise that. I'll think about it in a minute. Let's define this final height first. And then this is the distance between a velocity of 0 to a velocity of v final. So if I do the second velocity minus the first, this would be equal to v final minus 0, or just v final. Okay, and if I do this, then I can say from here to here, well, the acceleration is the same at all points. The acceleration is always, I'll be more generic here, v next minus v previous over whatever change in time. So if I rewrite these two heights in terms of acceleration, that's what I want to do, then for this first one, I would say v next would have been 0 minus v initial over the time would be t star for this first triangle. Let me actually shade it. Let's shade it in purple. Okay, so for the purple triangle, I can do acceleration equals 0 minus v initial over t star. And then I'll shade this other triangle in orange. And for that one, the same acceleration equals, in this case, it would end at v final, and my orange triangle starts with a velocity of 0. So v final minus 0 over the delta t in this case is the full time minus t star. If I solve for negative v initial, all I have to do is multiply t star over here, so let me switch back to the purple. I would get a times t star equals negative v initial. So I can just call this a t star for the height. And then for the height of the orange triangle, I can do similar. Multiply by t minus t star on both sides, and I get a times t minus t star equals v final. So I can write that as a substitute for the height over here. The height has a magnitude of a times t minus t star. Okay, now we can do something similar to what we did before. We can just use the formula for the height of a triangle, or not the height, the area of a triangle. We can use the formula for the area of a triangle. So for the area of this triangle, and we want this to be positive, it's going to be 1/2 base times height. So area of my positive triangle is going to be 1/2, base is t star, times height is, I want the height to be positive here because I want this to be a positive area. A times t star is a negative value. It's equal to negative v initial, and we already know v initial is positive. It starts above the horizontal axis. So in fact, I want to replace this. I want to substitute this as negative a t star. That way, I end up with a positive area. I guess another way we could have thought about it is we know the acceleration is going to be negative, so multiplying a negative acceleration by a negative sign ensures that this value ends up being positive. Okay, now for the negative triangle. A of the negative triangle is going to be, again, 1/2 base. So the base is t minus t star for the orange triangle, times the height. In this case, it's already positive, or is it? Hold on. V final equals a times t minus t star. Oh, no, hold on. Yeah, if it's equal to a oh, yeah, it's negative, which actually it should be. Okay, yeah. Times a times t minus t star. Yeah, no need to play around with signs there. This should come out negative since t minus t star is a positive value multiplied by the acceleration is a negative. Yeah, this should come out overall negative. Okay, now we are good to go. Unless, oh, then I guess this would actually be a plus. I'm taking a positive triangle plus a negative triangle. Yeah, there we go. So, yeah, this is the formula that we want to work with now. So my delta x, my total displacement, is going to equal a of the positive triangle plus a of the negative triangle is going to equal one half, I guess that's going to be, I'll just write it out first and then we'll simplify. T star times negative at star plus 1/2 of t minus t star times a times t minus t star. If we condense all this a little bit, then over here I'm going to have negative 1/2 a t star squared. I'll put the t star in parentheses just for clarity's sake. And then plus 1/2 a t minus t star, the whole quantity squared. Okay, now we're getting somewhere. I want to get a definition for t star, and that shouldn't be too hard to do. I can just take this over here and multiply by t star, divide by a, and that gives me t star equals 0 minus v initial, or negative v initial in other words, over a, which is similar to what we did last week, so this part was still right. If I go ahead and sub that in, at least for this one, I want to FOIL this one out first before I make my substitutions. I get negative 1/2. Actually, you know what? No, because I feel like the t star squared might cancel out. Let's not plug this in for t star just yet. Plus 1/2 a. Over here I'm going to have, let's see, if I FOIL this, I get t squared minus 2 t star plus t star squared, and I would have minus 1/2 a t star squared plus 1/2 a t star squared. Those would cancel out. this would cancel out with this. And that leaves me with this 1/2 a times t squared plus, distribute the 1/2 a to the second term, negative 2t t star. Okay, and then now I think is a good time to substitute t star with negative v initial over a, so that's going to be, I'll write it over here, 1/2 a t squared plus 1/2 a times negative 2t times negative v initial over a. Let's see. These two negative signs cancel out. This acceleration divided by this acceleration, that cancels out. The 2 cancels out with the 1/2 when we multiply them together. And all that's left is this t and this v initial. V initial times t. So I'm left with 1/2 at squared plus v initial times t, or if we write it in the traditional order, delta x equals v initial times t plus 1/2 at squared. There we go. That's the familiar looking second equation of kinematics proven through an alternative route. You can try and do this again with this graph flipped upside down, or even what I mentioned earlier with, where was it? Or you could take this graph and flip it upside down and see that no matter which case you have, whether your starting velocity is positive or negative, whether your acceleration is positive or negative, as long as you do the math right, you should end up with this every single time. The hard part is just, setting up the math and making sure you define everything correctly, because, when I was defining all of these heights and stuff, there were plenty of opportunities to be off by a negative sign, and I even caught when I wrote my delta x equation over there. I started with the assumption that it would be a minus sign, but then I had to revise it. So yeah, plenty of potential for mistakes, and you're probably going to make one, but as long as you catch it somewhere along the way, you should be fine. Okay, now we can talk about freely falling objects. What do I want to do with this paper? Yeah, whatever, I'll just add it to the stack. Maybe it'll be relevant later. Okay, now we want to talk about freely falling objects. We want to talk about the topic of free fall. So what does it mean for an object to be freely falling? Okay, so I'll just draw something, let's say a ball. Let's say I'm holding a ball, and then I release it. I let it drop. We know what happens through life experience. It starts to go down, it starts to develop a downward velocity, and over time, the longer it falls, the faster it falls. That's the part that we don't often get to notice in real life because we don't see the ball falling for long enough to notice that happening. Right? Usually we drop something from just a couple meters above the ground and it hits the ground and everything stops before we even have a chance to notice that the ball is actually getting faster when we drop it. It doesn't just start with some sort of initial speed. In fact, if you just let it go, its initial velocity is actually zero. Its initial velocity is actually zero, and gravity quickly changes that. But an object doesn't have to be literally falling for it to be in free fall. It doesn't have to be literally falling. I could just as easily throw an object upward. I could just as easily toss a ball upward with some sort of initial upward velocity, and it would go into the air, reach some sort of height, pause for a split second before coming back down and hitting the ground, and it would still be considered in free fall even on its way up. So what makes it free fall isn't the direction that it's moving. What makes it free fall is that the only thing causing its acceleration is gravity. So an object is in free fall when acceleration is solely due to gravity. When an object is under an acceleration solely due to gravity. That means, of course, that we have to assume that air resistance is not in play. That's a concept you may have heard of. Acceleration solely due to gravity. Now, what was I saying? Right, air resistance. So air resistance is a thing in real life, but for the sake of physics, we will often just neglect it because it'll make our calculations easier. And whether or not we're justified in doing that, I mean, we can do the math for certain objects that are small enough and dense enough and don't have a lot of surface area and aren't catching a lot of air particles, especially for very short falls like what we're used to seeing. Air resistance is not going to make that big of a difference, so the extra effort to adjust our calculations for that is probably not going to be worth it for what little difference it makes. But of course, if you're working for NASA or something, then yeah, you would have to actually take that stuff into account. So we will look at some extreme cases of air resistance, just a few special cases that are easy enough to do. Those of you doing AP Physics C, once we come back and review this topic, we'll talk about how to do calculus with air resistance, but if you can't wait for that, I do have a video from, what was it, 2 weeks ago, maybe, that had a couple of calculus-based air resistance problems, so you can look at that. It should be under my Office Hours with Al shelf on the main YouTube videos page. Anyway, so an object is in free fall if its acceleration is solely due to gravity. And the acceleration due to gravity is technically variable. The acceleration due to gravity is technically variable, so if this is the Earth, and I'm just going to draw some random shaped continents, not the most accurate representation of Earth, but we'll go with it. So if this is Earth, and, I'm standing somewhere on the surface, it depends on whether, for example, I'm standing at the top of Mount Everest. Let's pretend this is Mount Everest over here. And let me draw this person in a different color. This person standing at the top of Mount Everest is going to experience a lower acceleration due to gravity compared to someone who is, standing maybe at sea level over here. And a satellite that's just floating around, or even the moon itself, is going to experience even less gravity. The farther away you are from the surface of the Earth, the weaker the acceleration that you have towards the Earth. But for our purposes, we are going to mostly assume that we are close to the Earth, and specifically, we're going to assume that we're at a height that gives us an acceleration due to gravity equal to about 9.8 meters per second squared. That's what we call little g. You will see this on the AP Physics exam. Whenever you see g, unless you're told otherwise, you should assume this is the magnitude of the acceleration due to gravity near the surface of the Earth, without accounting for minute differences in elevation. We're just going to assume it's 9.8 anywhere on the surface of the Earth, regardless of how far it is above or below sea level. All for the sake of simplicity. Notice that this is the magnitude of the acceleration due to gravity. So g is always going to have a positive value of 9.8 meters per second squared. We will usually define down as the negative direction for objects in free fall. So we will say the acceleration is equal to the negative of g is equal to negative 9.8. And I know some of you probably have teachers that are a little bit pickier about this value. Some of you might have teachers who prefer that you use 9.81. As I said in the beginning, we are not going to worry too much about sig figs. You're not going to be graded on sig figs on the AP exam. You can worry about sig figs when and if you end up working for NASA or, just any important project where getting your numbers right is actually going to be critical with lives and money on the line. But yeah, if you want to use 9.81 because that's what your teacher uses, fine. I'm going to use 9.8. And in some special cases, I might even just round this to 10 for the sake of simplicity. You do actually get to do that on the AP exam. A lot of times, you'll even have a question that tells you, assume the value of g to be 10 meters per second squared. And if it's multiple choice, sometimes the answer choices, oftentimes actually, the answer choices will be written based on their calculations using 10 for g. So if you're in the habit of using one or the other and then you get something that's somewhat close to it in the multiple choice, just circle that answer as long as you're sure of all your other steps. Chances are they just chose to round it to 10 while you didn't, or vice versa. So other than that, everything else is pretty much the same. Equations are going to be exactly how they were for horizontal kinematics. We have v final is equal to v initial plus acceleration times time. In this case, the acceleration is negative g, so plus negative g times time. Or in other words, v final equals v initial minus gt, if you will. Your displacement is now a vertical displacement, so instead of delta x, I'm going to call it delta y equals v initial times t plus 1/2 of the acceleration, negative g, times t squared. This becomes delta y equals v initial t minus 1/2 gt squared, if you prefer to have it simplified like that. I would say that just because I already told you to memorize the equations of kinematics last week, I would say just remember the equations of kinematics as they were last week and just substitute the acceleration with negative g. That way you don't have to memorize these as a second set. I mean, over time and with practice, your brain will just quickly jump from this to this anyway. So yeah, don't memorize these three as a separate set. Just remember your basic three kinematics equations and you should be good to go. And then for our third equation, v final squared equals v initial squared plus 2 acceleration, which is negative g, times, in this case, the displacement is delta y. And if you simplify, that's v final squared equals v initial squared minus 2g delta y. So yeah, for the most part, it's the same kinematics equations that you're used to. It's just that your acceleration is often going to be this negative value. So you're going to see a minus sign where you would typically see a plus. But otherwise, everything else is still the same. You will sometimes still have a positive here because we might have problems where an object is launched upward and accelerated by like rocket propulsion. And then after some time, the engine gets cut off and then gravity takes over. So on its way up, it actually has a positive acceleration and you need to kind of split the problem into multiple phases. Kind of like that truck problem we did last week where it was speeding up, then coasting, then slowing down. Something similar can happen here. We could have cases where you have a positive vertical acceleration, so don't completely rule out the possibility of that. The other major difference, I guess, is that negative velocities are going to be much more common in vertical kinematics as opposed to horizontal, which means we really, really need to be careful for whenever we use, for example, this third equation, especially if we're solving for one of these v's, because the last step, if you're solving for v final or v initial from the third equation, is taking a square root. And you need to pay attention to the physics to figure out whether you're taking the positive or negative square root. And I see we have some comments in the chat. Let's see, it's variable but insignificant for an object at the surface of the Earth, correct? Oh, yes, thanks for reminding me. That's another thing that I should have brought up. The acceleration due to gravity, even though it varies depending on your elevation, for very, very small changes in elevation, like if I'm dropping a ball from 2 meters high, the change in gravity from 2 meters high to ground level is negligible. It's like, I don't know, 20 decimal places down. It's not going to make much of a difference. So yeah, for near the surface of Earth, we can assume the acceleration due to gravity to be constant. So thanks for reminding me of that. And let's see, usually you use 10 meters per second squared. Yeah, that's what a lot of people do because 10 is easy to work with. I like to use 9.8 just so that we have something that's a little bit closer to reality. Even though it's not that much of a difference, I do like the numbers to be somewhat realistic. And also because sometimes when you use 10, you get to make these weird cancellations and simplifications that you normally wouldn't be able to get away with. I can't really come up with an example off the top of my head. I'm thinking there was something during the simple harmonic motion unit where some people like to use this very weird cancellation trick, canceling something that isn't really supposed to be cancelable, and they can only get away with it when assuming a value of 10 for g, and even then just barely. So that's part of the reason I will try to use 9.8 for the most part. But you know, when you're doing like quick calculations, when you're estimating, or when you're doing a multiple choice test where time is of the essence, yeah, just use 10. Okay, now where did I want to go from here? I suppose now I want to talk about the initial velocity of a dropped object or a released object in general. So when an object is dropped, we have to be very careful when reading a problem. We have to be very careful about defining our initial velocity. An object's velocity, when an object is being carried by something else, when this pen is being carried by my hand, in my hand, it is currently at the same velocity as my hand. If I move my hand at 2 meters per second, the pen in my hand is also moving at 2 meters per second. If my hand is not moving, the pen in my hand is also not moving. So at the moment that my hand and the pen separate, the pen should be at that very initial moment, it should be at the same velocity that my hand was at the moment of release. So the pen actually does start off at 0 meters per second. Gravity then kicks in, and over a very short period of time gives it a downward velocity until it hits the table. If I throw the pen downward, that's a different story. If I throw the pen downward, then my hand at the moment of release was moving down with it. If my hand was moving down at, say, 3 meters per second, then the pen was also moving at 3 meters per second at the moment I release it, so its initial velocity would actually be 3, or -3, since we will often define down to be a negative. And this also works horizontally. If something is moving horizontally, if I'm, say, on a skateboard or in a moving vehicle or something, and then I drop like a tennis ball that's in my hand, whatever velocity I had on the skateboard, I guess we'll just call it V skate, whatever velocity I had there, the ball still has that velocity as well. So if I drop the ball, if I release the ball, it doesn't just go straight down. It's going to have a velocity that combines both the downward velocity that it gains due to gravity plus the horizontal velocity that it started with, and it will go down in a direction like this, except of course its downward velocity is changing over time, so it's not going to be a straight line curve, it's not going to be a straight diagonal. Instead, it's going to be this sort of curve, this sort of arc until it lands. And assuming little air resistance, when it does land, the guy on the skateboard will arrive right above where it lands. So guy on skateboard continues moving to the right, the ball moves down and right, and from the perspective of the guy on the skateboard, it looks as if the ball went straight down, but from the perspective of, somebody else over here looking at them, they see the ball actually moving in this sort of arc. We'll talk about that again when we look at projectile motion, because that's not really our topic. Gotta study biology now. Keep your content up. You're good. Thanks for the encouragement and take care. I will have these recordings posted for later in case people need them, so you're not really missing anything, but if you do have questions, I will get to them towards the end if they're not relevant to the immediate discussion topic. And yeah, feel free to come by, pop in for 5 minutes, 10 minutes, whatever, and yeah, take care, good luck with your biology, and I suppose I will see you later. Now, where was I? Oh, right, I was talking about, so the initial velocity of an object at the moment of its release is always just whatever velocity the carrying object was moving at the moment of release. Something very, very important to remember. We will do some problems that involve that once we get to it. Speaking of problems, I think we should actually get started. There are a couple of concepts that I still want to go over, but I think the best way to introduce them is through actual problems. So, this first problem is a classic. It says a ball is thrown vertically upward with a speed of 25 meters per second. They use the word speed a lot, and not velocity. You have to take the direction into consideration yourself to figure out whether that should be interpreted as a positive or negative velocity, assuming we're working in one dimension, which we are for this unit. So a ball is thrown vertically upward. A ball is thrown vertically upward with V initial is equal to 25 meters per second. I'm going to say that's positive 25. I'm going to define up as my positive direction and down as my negative direction. Part A is asking, how high does it rise? Part A is asking, how high does it rise? Or in other words, it's asking for the maximum height, H max. That's what part A is asking for. Part B is asking, how long does it take to reach its highest point? Time to reach the maximum height. I like to call this the time to rise. I like to call this T rise. You can call it whatever you want, but that's what I like to call it. I suppose some people would be happier calling it T max height or whatever. Whatever floats your boat, as long as you understand where the starting point and the ending point is for this time. As long as you understand, if you were, watching this situation unfold and you were holding a stopwatch, you would know when you start the stopwatch and when you stop it. It starts the moment the ball is thrown up. It stops when the ball reaches its maximum height. Or maybe it doesn't stop, but you hit the split timer button thing. Part C, how long does the ball take to hit the ground after it reaches its highest point? So this is what I like to call the time to fall back down, T fall. This is falling from the maximum height. And then part D is asking, what is its velocity when it returns to the level from which it started? So this ball is going to go into the air. It's going to reach some sort of maximum height, and it's going to come back down. And if it comes back down to the same level that it was thrown from, which is not what always happens, but if it comes back down to the level from which it was thrown from, this I'm going to call V final. What is that V final? So this is what I like to call a symmetric case. This is what I like to call a symmetric case. Not an official term, but this is how I like to refer to it, a symmetric case of free fall. What makes it symmetric is, one, the acceleration doesn't change at any point on the way up or on the way down. The acceleration is always negative 9.8. The acceleration goes against the velocity on the way up and goes with the velocity on the way down. Well, I guess it's more accurate to say the velocity goes against the acceleration on the way up and goes with the acceleration on the way down. Yeah, that would be a better way to phrase it. So, no changes in acceleration. The distance that you rise, the upward displacement to the maximum height equals the downward displacement from the maximum height. So equal displacements in terms of magnitude, opposite in direction, and equal amounts of time on the way up versus on the way down. The time to go up equals the amount of time to go down. We actually haven't proven that yet, but we will. We will prove that T rise is equal to T fall in general if you are working with a symmetric case. If you are working with rises and falls that are between the same two heights with the same acceleration due to gravity and with the same speeds at different heights. I use the word speed there because I'm referring specifically to the magnitude. We will make sense of that as we go. So first question, how high does it rise? What is the maximum height? So here we can take advantage of a, I guess, would it be our third? No, I guess it would be our second. No. Well, no, it would be our third known quantity. We know the initial velocity, and we know the acceleration. It's negative 9.8. And we have a third known quantity, which is for an object that's thrown normally upward under the influence of gravity, there's going to come a point where the velocity momentarily hits zero at the top before it turns around and starts developing a negative velocity. So we know this. I like to call it v top. Some people also like to call it v peak or v apex, whatever you prefer to call it. V top is equal to zero. V at the top or the peak or the apex or whatever you want to call it is equal to zero. It has to be because velocity changes continuously. That's how it works in the real world. You can't switch from going forward to backward without having at least some nanosecond long pause at the very least. You can't just change velocities on a dime. Even without changing direction, you can't change from moving 10 meters per second to 15 meters per second in the same direction without going through all of the velocities in between. We talked about that before. In the real world, changes in velocity must happen continuously, which means you have to visit all the values in between whatever velocity you are changing from and whatever velocity you're changing to. If you're changing from positive to negative or vice versa, you have to hit zero for at least a split second. And that happens up here. So now we have three pieces of known information. We know initial velocity, we know not final velocity, but a velocity that comes after the initial velocity. And we know acceleration. We know three of our kinematic variables, which means we can solve for the other two. So what do I want to use here? I guess the best thing to use if I'm solving for h max, the best thing to use would be the third equation. So v not final in this case. In this case I want v top squared as my second velocity equals v initial squared plus 2 times the acceleration, negative 9.8, times delta y. Now delta y would be, so starting from this starting height up to this maximum height, delta y is just equal to h max, positive h max, because it's an upward displacement. That will matter in a minute. We need to be careful when defining our vertical displacement because sometimes we're on the way up and other times we're on the way down. But yeah, delta y in this case is going to be equal to positive h max. Okay, let me go ahead and substitute. V top was 0, so that's out. V initial squared is 25 squared, which is 625. And I know that because I'm a nerd. And then 2 times negative 9.8 is negative 19.6. And then h max is the only thing left unknown. We can solve for it. So add 19.6 h max to both sides, divide both sides by 19.6. 625 divided by 19.6 gives me about 31.8877. I will round that to 31.89. So h max is 31.89 meters. Okay, part B, how long does it take to reach its highest point? We could have solved this before part A. We can just use the first kinematics equation for this. So we can do, first equation of kinematics was v final, which in this case is actually v top, is what we want to use as our second velocity. equals v initial, which is our positive 25, plus acceleration, negative 9.8, times time, which is our t rise that we're trying to solve for, and I see I did not make enough room for this. T rise. That's probably not even readable. I probably should have walled this off from the start. Okay, v top was 0, so 0 equals 25 minus 9.8 t rise. Add 9.8 t rise to both sides, divide by it, and we get 25 divided by 9.8 is about 2.55 seconds. So even if you're using 9.8, the great thing about being able to round it to 10 is that you can just quickly check your math. If you do 25 divided by 10, that's 2.5, so you would expect your answer to be somewhere around that, and 2.55 seconds does seem to be around that. I'll round it to 3 decimals. I tend to prefer 3 decimals for my time variables. So yeah, t rise, I guess I'll write it over here. T rise is equal to about 2.551 seconds, give or take. Okay, now we need to calculate the time it takes to fall. And I mentioned earlier that it should turn out to be equal to the amount of time it takes to rise. I should expect 2.551. Maybe it'll be slightly off because of rounding. But otherwise it should be the same value. And we can prove this generally. We can prove that this is generally true for symmetric cases anyway. So we can do, let's see, doing it the traditional way, not taking advantage of symmetry, we can say that we're starting from the top and going to the bottom. Actually, we could also just do starting from, the actual starting point and going to right when it lands. Either way works, but one might be easier than the other. I'm going to start from the top, and I'm going to use the second equation of kinematics. I'm going to use this. So I'm going to use delta y, which is from the top back down. So I'm working from here to there. I'm working from here to here. That's a downward displacement. If I'm starting here, if I'm using this as my starting point for the equation, using this as my ending point, my displacement is downward, so I have to be careful here and say that this displacement has to be negative h max. Negative, we calculated h max earlier as 31.89. So that's my delta y equals negative 31.89. Equals v initial times t. Since I'm starting up here, my v initial is actually v top for this one. So that's going to be v top, which is 0, times, whoops, did I write tot? V top times t fall plus 1/2 the acceleration, negative 9.8, times t fall squared. A lot of times, we tend to develop an avoidance to this equation because it tends to give us a quadratic that we need to solve if we're solving for time. Fortunately, v top is equal to 0. So this is gone. And now it's just a simple divide or multiply these terms over and take a square root. And since time is rarely ever going to make sense as a negative value for most problems that we will be given, it will just be the positive square root. So negative 31.89, let's see, half of negative 9.8 is negative 4.9. So negative 31.89 divided by this stuff, which amounts to negative 4.9. The negatives cancel out, which is a good sign. That means we did things correctly. After all, whatever this ratio is, it's supposed to be equal to t fall squared, and we can't really take the square root of a negative now, can we? So if you did this and you got a negative over here, that would have been your hint that you probably forgot to add on a negative sign for your delta y. Something to be very careful about. I see a new chat message. Hey, I'm planning to do AP Physics 1 2 semesters from now. I'm good with math. Do you have any specific tips? You might want to watch what I said towards the beginning of the first stream for this series from, like, what, 4 weeks ago now? You might want to go there. I talk a little bit about the math, and also I cover some algebra skills in the second stream, so you might want to watch those two. But basically, if you've got solid algebra skills and geometry skills, and you know a little bit of trig, sines, and cosines and whatnot, you should be good to go. And other than that, just pick up math tips as I go. When I do some of the practice problems that I do, I will often have some comments about strategies, things to do, like avoid plugging in values until the very end, because sometimes you'll discover that things cancel out and you don't need to waste time plugging them in from the get-go. Stuff like that. You'll just see me comment on as I do problems. So I don't know if that's the kind of advice you were looking for, but hopefully that helped regardless. Now, where was I? I wanted to do 31.89 divided by 4.9. 31.89 divided by 4.9. And that's about 6.508. I'm not going to round it yet. I'm going to take the square root of it as it is. And I'm getting 2.551. The decimals after the 1 look a little bit different from what I got before, but otherwise I'm getting exactly what I claimed I would be getting. Now, if you weren't expecting this to happen in advance, this is the point where I would expect you to be curious and ask yourself, these numbers seem to be related. Is there something here, or is this just a special case and the problem just happened to have the perfect numbers for this to happen? Is this generally true? This is the kind of mentality you want to have in order to start thinking like a physicist. This is where you go, hold on, this is a curious connection, there might be something here. Maybe I can prove that this is generally true, or I can prove that this was just a special case and it'll probably never happen to me again. Either way, we will look at this after we finish with this problem. Part D now is going to give us another curious outcome. So it says calculate what V final will be. So to get V final over here, we can do... We have a number of options. I could do the first equation from the very beginning when the ball was first thrown up to the very end when the ball comes down. And for that I would have to use the total time, the time to rise plus the time to fall. Or I could start from the top and go down to here, which I think would be easier because, you know, generally speaking, substituting one of your variables with a 0 makes the math go by a lot quicker. 0 tends to make a lot of our math easier most of the time. So I think that's what I'm going to do, but it would work, it would still work if you did it from here to here instead of from top to bottom. But yeah, I'm just going to do top to finish. So I'm going to use, since I know time and I know my starting velocity at the top and I know my acceleration, that would suggest using the first equation. So I'm going to do my second velocity, which I actually named v final, equals my first velocity for this interval, which is v top, which is 0, plus acceleration, which is negative 9.8, times the time for this period is the t fall that I just calculated, my 2.551. Now, what could ruin this is if you miscalculated this time, then that error would result in an error for part D as well. So that's something to take into consideration just from a sort of risk management perspective. If you can avoid reusing numbers you had to calculate in order to calculate other numbers, that just generally gives you a lower risk of one error turning into two errors, turning into three, but sometimes that's unavoidable. So, I wouldn't worry too much about this risk management strategy, just something to keep in mind. Anyway, negative 9.8 times 2.551 gives me negative 24.9998. That looks awfully close to negative 25, which is quite curious because our starting velocity was positive 25. V final equals negative 25 meters per second. I'm just going to go ahead and round it straight up to 25. So now I've got a second weird apparent shortcut that I might be able to use. My rule for shortcuts: if you are going to use them, make sure you can prove them. Never ever use a shortcut that you can't prove. Never use a shortcut that you don't understand the origin of. Because when you use a shortcut and you don't know where it came from and you don't actually understand it, you might use it under conditions where it doesn't actually apply. But now we need to expand further on the symmetric case. So it appears that when an object is thrown with some sort of initial velocity and it rises to some maximum height, then falls back down from that maximum height to whatever height it was originally thrown from, whether it was thrown from ground level or a couple meters above ground more likely, or whatever. As long as this, I'll call it delta y rise, is equal in magnitude to this delta y fall, and as long as there is no change in the acceleration at any point during this entire trajectory, it would seem that the time to rise equals the time to fall, and it would also seem that the final velocity is just the negative of the initial velocity. Can I prove this to be true? I can prove that second one actually quite easily. The second one is very quick and easy to prove. Well, there's a quick proof and then there's a not so quick proof. So the quick proof would be to just use the third equation of kinematics. V final squared equals V initial squared plus 2 times the acceleration times the displacement. Now the acceleration is negative g, not that it matters here because if I'm plugging in v final, this v final over here, which I forgot to label on my diagram, if I'm putting v final here and v initial here, then that means my starting point is here and my ending point is here. And that means the displacement that I plug in here is the displacement between this point and this point. What is the change in y between these 2 points? 0. They're at the same height. If I was standing with a ball in my hand and my hand was 2 meters above the ground and I threw it into the air and it came back down and I caught it, then its final location when I catch it is also 2 meters above the ground, and the difference between 2 meters and 2 meters above ground is 0. 0 change in height over the course of that duration that it was in the air. The overall change in height was 0. So yeah, this is just going to be a 0, which tells me v final squared equals v initial squared, and if I square root both sides, v final is going to be plus or minus the square root of v initial squared equals plus or minus v initial. Now, how do I know that it's the minus? Because of the physics. We already know that when the ball has a velocity of v final, or whatever this object is, we know it's going to be on its way back down. So we know from the physics that it's just the negative. We can strike out the plus. It's not plus or minus. We know for sure that it's minus. So v final equals negative v initial. This is easily proven for the symmetric case. Notice the requirement for this was that the delta y had to be 0. So this doesn't work if, say, I'm standing on the top of a building and I throw a ball upward, I stick my hand out over the edge of the roof, and then I throw the ball upward, and then it goes into the air and it lands somewhere, I don't know, 5 floors down. It's not going to work. It will work from here to here. Whatever downward velocity you have at this specific point is going to match the magnitude of the initial upward velocity here. That does work, but you can't say that this starting speed is going to equal the final speed when it lands on the ground somewhere over here. That's just not going to be true, and I think it should be fairly intuitive why that's the case. Okay, what about that other one? The time to rise equals the time to fall. How can we prove that that is generally true? I don't think red is the right color here. It looks too similar to the other 2 colors I've already used. Let's use blue. So proving that the time to rise equals the time to fall. Let's see. So let's go ahead and reuse what we did initially to calculate the time to rise. What we did was we used the velocity at the top, which we know to be 0, equals the initial velocity plus negative g times the time to rise. Let's do that. Let's go ahead and do that. Let's do v top, which is 0, equals v initial plus acceleration, negative g, times the time to rise. And if I substitute 0 over here, then I just get, I guess this minus gt rise can be added to both sides. So if I add gt rise to both sides, I get gt rise equals v initial. And if I divide by g, then the time to rise equals v initial over g. And this is somewhat intuitive if you stop to think about it. how much speed I have upward at the beginning divided by the amount of speed lost per second equals the amount of seconds it takes to lose all my initial upward velocity. If let's use 10 for the value of g, just to make this quick and simple. Let's say I threw the ball up at 30 meters per second and it loses 10 meters per second each second. That would mean it takes 3 seconds to lose 30 meters per second worth of velocity. So yeah, it's whatever the initial velocity is divided by the acceleration, or I guess you could call it deceleration in this case, due to gravity. That makes sense to me. I'm not surprised by this. So now we need to prove that this is equal to the time it takes to fall. Well, how did we calculate the time it takes to fall? We did the second equation. We did delta y equals, and then we started from the top to the landing, to the end. I don't want to call it top to bottom because technically the starting point is also at the bottom of the trajectory. I'll call it the end. From top to end, we did the second equation, which means we actually need delta y for this. Well, let's start with delta y fall equals, starting from the top, v top times t fall plus 1/2, acceleration is negative g, times t fall squared. V top is 0, so that's gone. But now I need to actually get delta y fall in terms of, well, let's see, I got t rise in terms of v initial and g, so in order to compare t fall to t rise, I want to get t fall in terms of v initial and g, which means I need to get delta y fall in terms of v initial and g. So let's go ahead and write the simplified version of this above equation, and then we'll figure out how to solve this delta y fall problem. Equals negative 1/2 g times t fall squared. Okay, well, how did we get delta y fall when we did the problem? We said it was the negative of the maximum height, and the maximum height we calculated in the first part of the problem using the third equation and substituting h max for our delta y rise. Over here, I'll just keep it as delta y rise. I don't have to call it h max if I don't want to. So yeah, let's actually do that. Let's do that calculation. Where do I want to do it? Let's do it over here on the right hand side, and let's do it in a different color too. Let's do green. Okay, so I want to get delta y rise, and let's use the third equation for that. So delta y rise, I want to calculate it from start to top. From start to top. So that means my quote-unquote final velocity is actually just my velocity at the top, v top squared, equals my start velocity is v initial, so v initial squared, plus 2 times negative g times, we'll just call it delta y rise this time, instead of calling it h max. V top squared, of course, is 0, and I can do, I guess I'll write 0 equals v initial squared minus 2g delta y rise first, and then add this to both sides, so I get 2g delta y rise equals v initial squared, and we know v initial is positive, so if we just take the positive square root, we are good to go here. V initial, or wait, no, actually, what am I saying? We're not solving for V initial. Divide by 2g. We're solving for delta y rise after all. Divide by 2g. So delta y rise equals V initial squared over 2g. Which, by the way, is something that you might want to remember, because this also gives you a direct relationship between how high an object rises relative to its initial speed. This might be useful in the type of question where I ask you, well, if I throw it at whatever meters per second, it rises to some height. What if I threw it at double that speed? Would it rise to twice as high, 4 times as high, 8 times as high? This would actually tell you, if you double the velocity, since you're squaring twice as much stuff, the square of 2 times whatever the original condition was would be 4 times as much height. If that didn't make sense to you, don't worry about it. We'll get to practice problems of that nature as we proceed through the course. Those types of questions are actually not that rare on the AP exam. We will get to them whenever we get to them. Anyway, going back to the problem at hand, now we have something we can substitute for delta y rise. I know that delta y fall is equal to the negative of delta y rise because I know my geometry. It's right there in front of me. So if I go ahead and go back to this equation right here, delta y fall is equal to negative delta y rise is equal to negative 1/2 g times t fall squared. If I go ahead and substitute v initial squared over 2g here, I get v initial squared over 2g with the negative out front equals negative 1/2 g t fall squared, and we're solving for t fall, so let's see, the negatives cancel out. If I multiply both sides by 2, the 2 cancels the 1/2 on the right hand side and cancels the 2 in the denominator on the left hand side, so those also get canceled out. Let me do red for this. So these get canceled out. And I would be dividing by g, which leaves me with a g squared in the bottom, and I think you can see where this is going. T fall squared equals v initial squared over g squared, and if I square root both sides, taking the positive root, because I know negative time doesn't make sense here, I would get t fall equals square root of v initial squared over g squared is just positive v initial over g. But wait a minute. If t fall equals v initial over g and t rise equals v initial over g, then that means that t rise and t fall are equal. So the time to rise equals the time to fall. And this also gives us a convenient shortcut. This allows us to calculate something called hang time. Hang time. Hang time is the total amount of time that an object is hanging in the air. Hang time, total time in the air. For symmetric situations, we can take a shortcut. For non-symmetric situations, we unfortunately have to do things the long and hard way. But hang time, total time in the air. Total time in the air. For symmetric situations, all I have to do is calculate the time to go up or the time to go down and multiply it by 2 and I'm done. So for symmetric situations, for symmetric cases. For symmetric cases and symmetric cases only, hang time equals t rise plus t fall equals 2 times t rise or 2 times t fall. Since t rise is equal to t fall, you can just take either one of them and multiply it by 2 and get your total hang time. For non-symmetric cases, t rise and t fall will be different, and the hang time will not just be 2 times either one of them. You will actually have to calculate the 2 separately before adding them in all those other cases. But yeah, there's your symmetric case. We have some shortcuts there, and I see I smudged my ink really badly over here. Sorry about that, but I guess you can always just rewind in case you were missing what it originally said. My goodness, my hands are covered in ink now. That's why we're supposed to write on the left-hand side of the page before the right-hand side. It's not just discrimination against left-handed people. Anyway, let's have a look at a couple more problems. How long have we been going? Almost 2 hours? Okay, we're actually moving at a better pace than I thought we would. We might actually be able to finish doing problems today then. Let's see. Don't want to do that one. Let's have a look at this one. A certain freely falling object requires 1.5 seconds to travel the last 30 meters before it hits the ground. From what height above the ground did it fall? And did I use... Yeah, I already used both sides of that page. Time for a new one. A certain freely falling object requires 1.5 seconds to travel the last 30 meters before it hits the ground. So interpreting the problem is already the biggest challenge of this problem for most people, I would imagine. Just reading it carefully. From what height above the ground did it fall? So if it fell from some sort of height above the ground, I'm going to assume it fell from rest. I'm going to assume it was like at the top of a cliff, and then it just ever so slightly tipped over and began to fall. Of course, it would be moving both horizontally and vertically, but we'll deal with that when we get to the projectile motion chapter. For now, we're just going to treat it as if it's only falling straight down. We don't want to worry about the horizontal part of its motion just yet. We will deal with that all in due time. So, assuming that its initial vertical velocity was 0, regardless of how fast it was rolling horizontally when it came off the cliff, or what did they say, building, was it? They didn't say if it was off a cliff or a building, but when it rolled off of whatever surface it was on, it fell some amount, and then part of its fall, the last 30 meters of its fall, so this right here, I don't even know if the 30 meters is just a small part of its total drop distance or if it's a larger part, so this drawing might not be to scale depending on what our numbers turn out to be. But this last 30 meters took 1.5 seconds. The last 30 meters took 1.5 seconds. we need to figure out from what height above ground did it fall. We need to figure out this total height. That's what we need to figure out. So let's see, what do we know? We know the acceleration is negative g, negative 9.8. So that's one kinematic variable we know. We are assuming the initial speed at the very top of wherever it dropped from is 0, so that's two known values. We don't know what this is. We don't know the total time. We do know the time it takes to fall the last 30 meters. We do know that that's 1.5 seconds. But do we actually have... I guess what I would have to do here is divide it into 3 different velocities. So we're going to have the velocity at the top. I'm going to call that V0. I'm just going to use numbers to keep everything organized. Once it's over here, I'm going to call that V1. And when it lands, when it hits the ground, or rather the split second before it hits the ground, because the ground, once it makes contact, will actually change its velocity. So we'll say a nanosecond before it hits the ground, it will have a velocity of v2. And by the way, since we're talking about that now, I might as well bring it up. If you are ever asked what velocity an object has when it hits the ground, you don't take the collision with the ground into account. You're not expected to factor that in. They're generally asking you what speed did it have, what velocity did it have, just one split second before it actually made physical contact with the ground. So that's something to keep in mind. You do not have to, unless they give you more information, like this next problem that I have lined up. Unless they give you more information about collision with the ground, if they ask you for velocity of an object when it hits the ground, they mean the split second before contact is actually made. Anyway, I think actually I can just solve this from here to here, because I don't know V1 and I don't know V2, but I do know the time between these 2 points, and I do know the displacement is not 30, but negative 30, since it's on the way down, and I know the acceleration due to gravity. So yeah, actually we can just solve from here to here. Which equation do I want to use? I know time, I know displacement, I know acceleration, and I want to know either my V1 or my V2. The second equation sounds like it would be the best choice for this, and let me switch off of orange. Gotta remember that doesn't end up looking too good on the video near the top for some reason. Delta y is equal to, I guess in this case it would be V1 times, what do I even want to call it? I guess I'll call the time it takes to fall from top to here, I'm going to call that T1. And I'm going to call that 1.5 seconds, I'm going to call that T2. So it's going to be V1 times T2 plus 1/2, the acceleration is negative 9.8, times T2 squared. And delta y, come to think of it, I should call that delta y2 from here to here, and this will be delta y1. So delta y2 is negative 30. Remember that negative. Very common mistake. That's the only thing that makes freefall more challenging than horizontal kinematics, is just keeping track of your signs, remembering up is positive, down is negative, unless you're feeling dangerous and you want to flip all the signs. You actually can do that and the math will work out, but why would you do that? Just why? Anyway, negative 30 equals v1 times t. I don't know v1. T2 I do know is 1.5. Half of negative 9.8 is negative 4.9. And then t2 squared is 1.5 squared. Let's see. I'm going to add 4.9 times 1.5 squared over to the negative 30. So negative 30 plus 4.9 times 1.5 squared equals negative 18.975. Negative 18.975. This sounds like it might divide very nicely when I divide it by 1.5 here. So if I divide by 1.5, I get negative 12.65. I get V1 equals negative 12.65 meters per second. Okay. And yeah, assuming that V0 is equal to 0, because without making that assumption, I don't know how else you would be expected to solve this problem, we can now do an equation from here to this not even halfway point, but whatever this break point is. And what are my known values? I know V0, I know V1, I know the acceleration. That's the saving grace for most of these free fall problems, is that you usually know the acceleration unless they give you something where you want to solve for the acceleration on the moon or Mars or whatever. But a lot of the time, the acceleration is known, which tends to make the math easier because all three of our kinematics equations involve acceleration. We already went over the worst case scenario last time for your kinematics equations is when you don't know your v initial nor your acceleration. That's the worst case scenario because those two unknowns exist in all three of your equations, which would mean that you'd be pretty much forced to use two of them together, unless you want to use that fourth kinematics equation that I argued was not entirely necessary. But anyway, I'm rambling too much. We want to figure out what this h is. So I guess third equation would be the best way to go about it so that we avoid having to solve for t1. Third equation, I would do, I guess we'll call it delta y1 is equal to v0 times, oh wait, no. I said third equation and I started writing the second one for some reason. v1 squared equals v0 squared, there we go, plus 2 times negative g times delta y1. v1 squared, we've got 12.65. If we square it, it doesn't matter that it's negative. Once you square it, it becomes positive. So that's 160.0225. I think I'm going to keep that as is. It feels too clean to just round. Equals, that's just going to be 0. And then that's negative 19.6 times delta y1. 160.0225 divided by negative 19.6 gives me negative 8.164. I'll just round it to negative 8.16. Delta y1 equals negative 8.16. Am I surprised that it's negative? No, we should be expecting that. We should be expecting negative 8. Well, we should be expecting a negative value because it's a downward displacement. So yeah, I am not surprised at all that it came out to be negative. That's actually reassuring. 8.16 is a lot smaller than this 30, so clearly my drawing was not to scale. A drawing that would have been to scale would be something more like this, with my delta y1 over here, and then my delta y2, my 30 meters, being about that big in comparison. But, you cannot be asked to draw things to scale if you don't know the ratios of these things to begin with. If that's information you have to solve for, then they cannot ask you to draw things to scale until after you've made the calculations, at which point it kind of defeats the purpose of even having a drawing. So, yeah, let's not worry too much about that. Draw things to scale only when you have enough information to draw things to scale, and if you don't, they're not going to be unreasonable with you. They're not going to expect you to do something that you don't actually have enough information to do. Okay, I think that takes care of the problem, right? From what height above the ground did it fall? No, we're not done yet. The total height, if it dropped 8.16 meters here and 30 meters here, then the total, I need to add those together, 30 plus 8.16, h is going to be absolute value of delta y1 plus absolute value of delta y2 equals 38.16 meters. Approximately. And that takes care of that problem. This next one is another favorite that I like to give to my students. It says that traumatic brain injury such as concussion results when the head undergoes a very large acceleration. Generally, an acceleration less than 800 meters per second squared, lasting for any length of time, will not cause injury, whereas an acceleration greater than 1,000 meters per second squared, lasting for at least 1 millisecond, will cause injury. So 800 meters per second squared, no injury, no long-term injury. 1,000 meters per second squared and 1 millisecond or longer causes injury. And this is the magnitude of the acceleration that we're talking about. Whether it's positive or negative is not entirely relevant when it comes to determining whether injury is caused. It does matter to us because we're physicists, or at least physicists in training. Suppose a small child rolls off a bed that is 0.4 meters above the floor. If the floor is hardwood, the child's head is brought to rest in approximately 2 millimeters. If the floor is carpeted, this stopping distance is increased to about 1 centimeter. Calculate the magnitude and duration of the deceleration in both cases to determine the risk of injury. Assume that the child remains horizontal during the fall to the floor. Note that a more complicated fall, such as falling at an angle, could result in a head velocity greater or less than the speed you calculate. So assuming the person just rolls over and falls flat, they want us to do the calculation. Starting to get cloudy outside. Let me flip on the lights. I noticed while reviewing the footage from last week that it doesn't really make that much of a difference on the video, but it makes a difference to me at the very least. You wouldn't want me teaching without seeing what I'm actually writing. I mean, I can still see it, but not with as much clarity with lights off than with lights on. What color do I want to use here? What have I not used in a while? Let me see. I guess I haven't really touched the navy blue in a while. Let's grab that one. Okay, so we had the initial height. I guess I will draw it over here. So child rolls off of a bed. And they are 0.4 meters above the floor. 0.4 meters above the floor initially. Then they're going to have a second displacement once they hit the floor. It's going to be much smaller, but I'm going to draw it off scale here. Just going to draw it a little exaggerated so that I actually have enough room to write stuff. This I'm going to call delta y2. And in one case, it's going to be 2 millimeters for hardwood. In another case, it's going to be 1 full centimeter for carpet floor. So that's going to be delta y2, and then my delta y1 is going to be negative 0.4. So let me write that up here. Delta y1 equals negative 0.4, and delta y2 equals either negative 2 millimeters or negative 1 centimeter of additional drop. So they drop 0.4 meters and then they drop a little bit more. And I want to separate those two drops because those two drops are going to occur under different accelerations. Dropping until just before making contact with the floor, your acceleration is just negative g. But after making contact with the floor pushes up on you. It fights back against this negative g, and it fights back hard enough that it actually overcomes it, and you end up with a total acceleration of something minus the g equaling whatever positive acceleration is left over. And that leftover positive acceleration is what we're trying to calculate and compare to 800 versus 1000. So I think we have everything we need. V initial, or I guess I'll call it V0. When you start here, you're at V0, which I'm going to call 0. They roll off with no upward or downward velocity to begin with. Then they, just before hitting the floor, they reach some sort of velocity due to gravity, V1, we don't know what it is yet. And then, once the floor does its work, it eventually brings them to a stop. That's what we're going to call V2. That's also equal to 0. They gain some speed, they hit the floor slows them back down and brings them to a stop. So this is basically a two-phase problem, not too different from the truck problem that we saw last week. Well, I guess we saw multiple truck problems. The truck problem that had the 3 phases, the speeding up, then coasting, then slowing down phases. That's the one I'm referring to. Okay. Let's go ahead and set up our calculation for V1. I imagine that's the first thing that we're going to need. We have V0. Actually, hold on. What I want to do is organize my information. So I've got V0, V1, acceleration 1, time 1, and displacement 1 for the first phase of the motion. And for the second phase, it will start with a velocity of V1 then go to a velocity of v2 under an acceleration of a2 for a time t2 under a displacement delta y2. Okay, v0 I know is 0, v2 is also going to be 0. v1 we can calculate later. a1 we know is negative g is negative 9.8 meters per second squared. t1 we don't know yet. Delta y1 we know is negative 0.4 meters. And then delta y2 is going to take on two different possible values, which we do need to convert to meters, by the way. That is something that needs to be taken care of. So yeah, we've got 3 of our kinematic variables for the first phase, which means we can calculate the other 2. Once you have 3 of the variables, you can get the other 2. So I'm going to use, which equation involves these 3? Do I have an equation that does that? Yes, that would be the third equation, which is convenient because it will give me v1 without having to calculate t1. In fact, I don't think I ever need to calculate t1 for this problem. You could if you were curious, but we don't need it. So v1 squared, whatever it is equal to v0 squared, which is just 0, plus 2 times a1 is going to be negative 9.8 times delta y1, which is going to be negative 0.4. Here's another point where if you miss your negative signs, you're going to get the wrong results, because if you forgot the negative on your 0.4, you're going to end up with some negative result over here, and you would end up having to take the square root of it, and that would be the moment you realize you did something wrong. So I guess in this part of the one-dimensional motion unit, if you find yourself taking the square root of a negative, that's your hint that you should probably check your displacements, especially for vertical problems. Your displacements and the signs on your velocities, because a lot of times problems will say speed and they'll give you the magnitude, and you have to put 2 and 2 together and realize that it's moving downward and add the negative sign yourself. I know I've probably rambled on this point too many times for most people's liking, but it's important. It's a very, very common mistake. I mean, even I make that mistake from time to time, and I've been doing this for like a decade and a half now. So let's grab our calculator. 2 times 9.8 times 0.4 is 7.84. So that's v1 squared. v1 squared equals 7.84. And if I take the square root, here's another place you want to be careful. I get 2.8. But am I taking the positive root or the negative root? v1, my velocity, or the child's velocity rather, just as they're about to hit the floor, is a downward velocity. For us, we use a negative sign for downward. So I'm going to have v1 equals the negative square root of 7.84 equals negative 2.8 meters per second. Negative 2.8 meters per second. Okay, so that takes care of v1. Now we have 2 pieces of information, and technically we also have the third piece of information here. We just have to convert these to meters so that our units agree with each other. So yeah, let's do the first one, negative 2 millimeters. Let's convert that to meters. A millimeter is 1/1000th of a meter, so 2 millimeters is 2 thousandths, or 0.002. Let me switch colors for this. What do I want to use? gravity. So if I know this and this and this, and I'm trying to solve for the acceleration, I guess I would just use the third equation of kinematics again. Except this time it's between here and here instead of here to here. Okay, third equation of kinematics. Start with V1, end with V2. So V2 squared equals V1 squared plus 2 times A2 times delta Y2. So that's going to be 0 equals V1 squared. Well, it was originally 7.84 before we square rooted it. So I guess just this once, if you had kept this as 2.8 and forgot the negative sign, you would have gotten away with it. But, you know, don't get too complacent just because this problem spared you. Other problems will not. And then plus 2 times acceleration 2, which we actually don't know, times delta y2. Our first version of this delta y2 is going to be negative 0.002 meters, right? 2 millimeters, 2 thousandths of a meter. Okay, that's going to be, when I multiply the 2, it becomes negative 0.004 of A2. Add 0.004 A2 to both sides, and I'm left with 7.84 over 0.004. So A2, at least in the first version, is 7.84 over 0.004. 7.84 over 0.004. And that's 1,960. That's 1,960 meters per second squared. Now, some of you are wondering, do we need to subtract gravity out of this? And the answer is no, we don't. This has already taken care of that for us. This is the 1960. This 1960 is what's left over after the 9.8 from gravity has already been subtracted from it. And that will start to make more sense once we get to the force chapter. We will see how gravity combines with other forces, in this case the upward force from the floor, which we call a normal force, again something to be explained later, and how those forces combine to determine the acceleration of an object. This acceleration already has all of that calculation accounted for. So no, we don't have to modify this. And even if you did modify it, the point of the question is, if it's over 1,000 meters per second squared, then test it to see if it lasts for more than a millisecond, and if it does, it causes injury. Adding or subtracting a 9.8 here isn't going to change the fact that we have to do this time test anyway. So let's go ahead and calculate the time for this. I can use, I guess first equation would be the most convenient here. So if I use the first equation of kinematics, I can do V2, which is 0, equals V1, which is negative 2.8. Now this negative matters, so like I said earlier, don't rest too easy just because you got away with forgetting the negative sign for this first part. 0 equals negative 2.8 plus the acceleration of 1960 times t2. If I add 2.8 to both sides and divide by 1960, t2 is equal to 2.8 divided by 1960 is 0.001428. T2 is equal to 0.001428, and that's in seconds. If I convert this to milliseconds, move the decimal 3 places, that's also equal to 1.428 milliseconds, and they said acceleration of 1,000 or more lasting for 1 millisecond or longer, this is definitely longer than a millisecond, causes injury. So falling on hardwood floor, surprising to no one, I would hope, can cause traumatic brain injury. Okay, now let's compare to the carpet floor. So with the carpet floor, the only thing we need to change is the value of delta y2. So instead of -2 millimeters, we want it to be -1 centimeter. So over here, replace this -0.002 with 1 centimeter is 1/100th of a meter, so 0.01. So replace this with -0.01 and do the math again. And if I do that, then let's see. -0.01 times 2 is -0.02. Add 0.02 of A2 to both sides. And in the second version of the problem, in the carpet version, we get 7.84 divided by 0.02 gives me A2 is equal to 392 meters per second squared. And they told us that an acceleration of 800 meters per second squared or less will cause no long-term injury, so we're done. We don't have to calculate the time like we did for the 1960 because the acceleration is not big enough to cause injury for any duration of time. All right, that takes care of our, what is that now? Our third kinematics example problem. Let's grab maybe 2 or 3 more and then we can call it a day. And then next time I think the plan will be to cover a couple of more challenging problems in both horizontal and vertical. And then after that we will move on to the topic of projectile motion. We might actually do that in next week's lecture anyway, depending on how long those problems last. So yeah, let's move on. I still have the back side of this page to work with. Okay, this next one will capitalize on what I was talking about earlier about the velocity of a released object compared to the releasing object. So it says a small mailbag is released from a helicopter that is descending steadily at 1.5 meters per second. After 2 seconds, part A, what is the speed of the mailbag? And part B, how far is it below the helicopter? And then part C says, what are your answers to parts A and B if the helicopter is rising steadily at 1.5 meters per second instead? So let's reread all that and piece it together bit by bit. What color do I want to use here? I think I haven't really used this light blue in a while. So small mailbag released from a helicopter that is descending at 1.5 meters per second. Here's my best attempt at drawing a helicopter. Something like that, and then it's got the propeller. It's going to look something like that, and then you've got, your front window. Okay, there you go. So that's a helicopter, and it is moving at a steady, in other words, constant velocity. V helicopter is, since it's downward, I'm going to make it negative 1.5 meters per second. It's descending steadily at 1.5 meters per second. A small mailbag is released from it while it's descending. So a small mailbag is released from it while it's descending, I'm just going to use the message icon to represent the mailbag. It says, after 2 seconds, what is the speed of the mailbag and how far is it below the helicopter? So time equals 2 seconds. And they're asking, what is the speed of the mailbag? Speed, not velocity. Speed of mailbag. And the second part is asking, how far is it below the helicopter? How far below the helicopter? Seems like a very simple premise, but there's a lot here that you can miss if you do not interpret the situation carefully. Drawing a good diagram is everything, especially in mechanics, and to some extent also electromagnetism, and optics, and I guess most of physics, really. I guess thermodynamics is the least diagram friendly, in my opinion at least. It's not really easy to illustrate the concept of heat and energy moving. But now I'm rambling about unrelated topics. I forgot what I wanted to say. Well, while I remember, I might as well take a sip of water since it's been a while since I did that. Okay. Oh, goodness. I really need to be more careful with the way I drink my water. I think that's the second time this weekend I almost choked on my water. Anyway, what I was going to say. The first slip up that students make with this type of problem is that they assume that the initial speed of the mailbag is 0. That is not true. We went over this what was it, an hour ago at this point? I don't even remember. This mailbag was on a moving helicopter before it was released. It was moving with the helicopter at 1.5 meters per second downward before it was let go. So the initial velocity of the mailbag, I'm going to call it Vm, initial, is also negative 1.5 meters per second. The initial velocity of a released object is the velocity of the releasing object at the moment of release. You can actually just test this out in real life. When you throw a ball, when you throw anything, the velocity with which the object leaves your hand when you let go of it is whatever velocity your hand was moving with the object just a moment before release. You can practice it, you can test it out in real life, you can convince yourself that this idea makes sense. You don't have to just take my word for it. That's the great thing about mechanics, is that you can test a lot of this stuff in the physical world and convince yourself it makes sense. Sure, when we teach mechanics, we make simplifications, like we ignore air resistance for the most part, and that's something you encounter in real life that might mess up a little bit, that might slightly mess up your observations, but for the most part, you can test most of these ideas that you're learning just through your five senses, just through experimenting at home. Just please don't break any walls or anything while you're experimenting. I don't want your parents blaming me for costly household repairs. I once had a student that did that. They did the experiment with the moment of inertia thing, or not moment of inertia, the conservation of angular momentum trick where you sit in a spinning chair. I will describe it when we get to that chapter. But yeah, let's just say he spun too fast and somehow ended up kicking a wall so hard that he broke a hole in it. So yeah, be careful when you're experimenting. Where did I want to go from here? Right, so we have the initial velocity of the mailbag, and once it's released, there's nothing preventing gravity from dragging it down. So from the moment of release to, I guess, whenever it lands on the ground, its acceleration is going to be negative 9.8. So we have v mailbag initial is negative 1.5. V mailbag final, we don't know yet. Although that's the first thing that they asked for, kind of. They want the magnitude of it. The acceleration of the mailbag is negative 9.8. The time that the mailbag is falling was given to us as 2 seconds, and the vertical displacement of the mailbag we don't know yet. We know 3 of these 5 variables. That's enough information to calculate the other 2. All you need is 3. 3, 3, 3, 3, 3. So let's calculate the speed of the mailbag. We can actually do that using the first equation of kinematics. V mailbag final equals V mailbag initial plus the acceleration of the mailbag times the time. And that would be V mailbag final equals negative 1.5 minus 9.8 times 2. So negative 1.5 minus 19.6, negative 20.6, negative 21.1. I think I would have felt a little embarrassed if I reached for the calculator on that one. All right. So then take the absolute value of that, and the speed of the mailbag is 21.1 meters per second. Okay. Next, the question is, how far below the helicopter is it? Well, clearly we need to calculate delta y of the mailbag here, but there's a twist. There's something that a lot of students will miss here. See if you can figure it out while we solve for delta y of the mailbag. Delta y of the mailbag, I'll just use the second equation here, equals v mailbag initial times t plus 1/2 the acceleration of the mailbag times t squared equals negative 1.5 times 2 plus 1/2 negative 9.8 times 2 squared. Okay, so that's going to be negative 3, and then minus 4.9 times 4, that's minus 19.6. So minus 3 and minus 19.6 is negative 22.6 meters. This is the point where a lot of students will say, oh, the mailbag is 22.6 meters below the helicopter. Wrong. What is wrong with this? What's wrong with this is that we forgot that the helicopter is also still moving. The helicopter is also still moving. The helicopter and mailbag were moving together. The mailbag gets released. The mailbag starts to accelerate downward, so it quickly starts to gain some distance from the helicopter, but the helicopter is still going down. So now we actually have to calculate delta y of the helicopter. Delta y of the helicopter equals velocity of the helicopter times time plus 1/2 the acceleration of the helicopter times the time squared. The helicopter and mailbag move according to the same timer. We tracked their motion with the same starting and ending time for those 2 seconds. So t is still 2 there. The acceleration of the helicopter is 0. Acceleration of the helicopter is 0, so that whole second term goes out. And so delta y of the helicopter is equal to negative 1.5 times 2 is equal to negative 3 meters. So the helicopter went down 3 meters in the same amount of time that the mailbag went down 22.6 meters. So the gap between them is negative 3 minus negative 22.6 is 19.6 meters. Delta y helicopter minus delta y mailbag. If you don't want to think about the order of subtraction, you can just subtract in whatever order and put absolute value bars in between, or not in between, around it, rather. Put this difference in between absolute value bars is what I was trying to say. And yeah, you get absolute value of negative 3 minus negative 22.6 equals 19.6 meters. That is the gap between the mailbag and the helicopter after 2 seconds. Okay, so that's parts A and B. Part C says, what are your answers to parts A and B if the helicopter is rising steadily at 1.5 meters per second instead of falling? So do the same problem again, but this time V helicopter and V initial of the mailbag is positive 1.5 meters per second. Well, part A will change, but part B is going to surprise us a little bit. Part B will have a little surprise for us, but let's look at part A. So calculating the speed of the mailbag. We can just redo what we did up here, except flip these to positive values instead of negative. So V mailbag initial is now going to be positive 1.5 meters per second. So V mailbag final equals positive 1.5 plus negative 9.8 times 2 minus 9.8 times 2. That's minus 19.6, and 1.5, that's minus 18.1 meters per second. So speed after 2 seconds is 18.1 meters per second. And come to think of it, I should have written my answer for part B over here, 19.6 meters below the helicopter. Okay, so nothing remarkable that stands out here? Well, I guess there is something that stands out. Notice that the difference is exactly 3 between 21.1 and 18.1. The difference is exactly 3. The difference is just the difference between the initial velocity when falling versus the initial velocity when the helicopter was rising instead. From negative 1.5 to positive 1.5 is a change of 3 meters per second. But the second part, this minus 9.8 times 2, this second part didn't change. The only thing that changed is this first part. So it actually does make sense that the change in the final speed of the mailbag is directly related to the change in this initial speed, and only the change in the initial speed. We didn't change anything about the time that gravity was acting on the mailbag, or the strength of the gravity for that matter. Okay, and then the second part. This one might surprise you. How far below the helicopter will it be? Well, and now we know to calculate how high the helicopter rises. So delta y of the helicopter is equal to positive 1.5 times 2 plus nothing, because there's no acceleration for the helicopter. And that equals positive 3 meters. Okay, what about delta y of the mailbag? It's going to be positive 1.5 times 2 plus 1/2 of negative 9.8 times 2 squared. Half of negative 9.8 is negative 4.9 times 4 is negative 19.6. We've got 3 minus 19.6 is negative 16.6 meters. That makes sense to me. So yes, the mailbag had an initial upward velocity in the case where the helicopter is rising, and you can actually play with this at home. If you carry a pen or something and you raise your hand up and you let go, especially if your hand is moving fast enough, you can see it go up a little bit before it comes back down. I can't do it too well here because I don't want my pen to bump into the camera. But, you know, if you flick your wrist up and then let go of an object, or don't even flick your wrist up, just raise your hand, maybe start from the ground, raise your hand up and then let go of an object in your hand, and move your hand sideways so that it doesn't block the object. Not that I think it would. No, actually it shouldn't matter. Yeah, you don't need to move your hand out of the way, as long as you don't stop your hand, is the caveat. But yeah, if you carry an object, put your hand on the ground, and then lift your hand up quickly and eventually let go, you can see the object rise a little bit before it falls back down, in case that doesn't feel convincing to you that the mailbag would rise first before falling. But yeah, the mailbag will have an initial rise, and then gravity kicks in and pulls it back down while the helicopter continues to lift upward. And so we've got the mailbag ends up 16.6 meters below where they started to separate from each other. I guess I can draw that here. Mailbag ends up 16.6 meters below where they were at the moment of separation, while the helicopter ends up 3 meters above. And if we do this same calculation here, delta y helicopter minus delta y mailbag, and take the absolute value, we get delta y helicopter, which is 3, minus negative 16.6. You can even see it more clearly in the drawing. That's 19.6 meters again, huh? Why is that happening? Why on earth is this happening? So you're telling me that maybe the initial speed of the helicopter or the initial speed of the mailbag and also the constant speed of the helicopter doesn't really matter as long as the speed of the helicopter is constant. It doesn't matter what direction, it doesn't matter what the magnitude is. Is that what we're trying to say? We can actually prove that this is the case. Let's not substitute a value for v helicopter. Let's just call it v helicopter in general and see what happens. So if I calculate delta y helicopter now, delta y helicopter is just equal to v helicopter times t, plus nothing, because again, the acceleration part of the second equation of kinematics doesn't apply to the helicopter since it's not accelerating. Okay, what about delta y of the mailbag? Delta y of the mailbag, well, v initial of the mailbag is just v helicopter times the same t plus 1/2 acceleration of the mailbag times t squared, or I guess I can replace this with negative g. If I do delta y helicopter minus delta y mailbag, if I do delta y helicopter minus delta y mailbag, I'm doing v helicopter times t minus all this, v helicopter times t, whoops, t should be up here, not in the subscript, v helicopter times t, plus 1/2, that's going to be minus 1/2 g, if I replace my acceleration with negative g, times t squared. V helicopter times t minus v helicopter times t cancels out. The minus and the minus cancel out, and I'm left with the distance between the helicopter and the mailbag after t seconds is just equal to 1/2 gt squared. And when you think about it, that does kind of make intuitive sense. That does kind of make intuitive sense. The only difference between the motion of the helicopter and the motion of the mailbag is that the mailbag has an acceleration due to gravity and the helicopter doesn't. Everything else about them is the same. Their initial velocity is the same. The amount of time we're tracking their movement is the same. So any difference in their displacements should be explained by the one and only difference they do have in their motion, the fact that one of them is subject to the acceleration of gravity while the other one is not. Well, okay, technically the helicopter is also subject to gravity, but it counters that gravity using its propellers. But you know what I'm trying to say, I would hope. So any distance created by the helicopter and the mailbag has to do with only what planet you're on, what your gravity is, and also just how much time has passed. Those are the only two factors that can create a difference in position between this helicopter and mailbag. That was, of course, not asked of us in the question, but this is kind of the mindset that I would hope you guys develop when you look at problems in your textbooks. Don't just solve the problem that the textbook is asking. If you see something curious, see if you can explain it to yourself. See if you can do a little bit of extra work and see if maybe you've discovered some sort of pattern, something that you can take away and use maybe in a future problem. And even if it's not something that you're ever going to use in a future problem, I don't think I've ever encountered another problem where I have to use this in particular, but you still want to gain the experience. You still want to gain that sort of problem-solving experience from this. Even if the equation you derive itself is not going to be used again, the algebra skills that led to this, the thought process, that sort of thinking style is something that you can transfer to other problems. So be on the lookout for that. Okay. I think... Do I want to do one more? You know what? Since it's already looking like next week is going to be all problems focused, I think we can just call it a day here. But I'll at least do what I did last time and just give you something to think about over the week. So the next problem that we will look at when we start next week is this one, which says, a model rocket is launched straight upward with initial speed of 50 meters per second. With initial speed of 50 meters per second. It accelerates with a constant upward acceleration of positive 2 meters per second squared. So it has an acceleration. Let's do that in a different color. Acceleration is 2 meters per second squared in the upward direction, and this already has gravity factored in, so you don't have to worry about that. Gravity has already been subtracted from this. Let's see, where was the problem? Until its engines stop at an altitude of 150 meters. What is the maximum height reached by the rocket? How long after liftoff does the rocket reach its maximum height? And how long is the rocket in the air? So this thing goes up, 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 up. At some point, its engine gets cut off, and once the engine is off, this acceleration of 2 meters per second squared is gone, and now the only thing causing acceleration for this object is gravity, because we're neglecting air resistance. So it will continue going up because it has already built up some upward velocity, and it'll continue going for a while, probably way, way longer than what I'm drawing here. It'll reach its peak at some point and then fall back down. And it's asking you how high it rises, how long it takes to reach its maximum height, and what was the third part? How long is it in the air in total? This is not a symmetric case like what we saw in our first example problem. You've got a different acceleration on the way up versus on the way down. There is symmetry from this point to this point, since all the way from here to here, you've got equal amounts of displacement, upward versus downward, with a constant acceleration being negative g. So you could apply the symmetry stuff we learned from this point to this point, although I'll give you a hint right now, you're not really going to need it. In fact, taking advantage of it will probably lead you towards the wrong path to solving this problem and make it take longer than it should. And it's already going to be a pretty long problem, especially if it's your first time doing this type of problem. But anyway, I will let you guys think about that one over the week. Also, definitely look at the course plan linked in the description and see some of the exercises that I listed over there, just to get some general practice with basic free fall problems and horizontal motion problems, since I forgot to tell you guys to try those last week. And yeah, I think that'll be it for today, at least for the physics students. I'm going to take a 15-minute break. Once I'm back, I'm going to continue what I did for last week's office hours session, which is the topic of Riemann Sums. Physics C students, you might have an interest in that, although I will be reintroducing that topic later once we get to the end of the Physics 1 stuff and go back and reinsert the calculus into it for the Physics C students. So It's up to you. If you're in a hurry to learn some calculus, then you may want to stick around and see that, although you might be confused if you didn't watch last week's video on Riemann sums. So that's all stuff for consideration. Anyway, that's enough rambling from me. Class dismissed. I will see you guys next week. All right, let's do another sound check and see if things are still working as they were before. That does appear to be the case, and do I see my hand there? Okay, my hand is visible. All right, sound check done. Let me put away the headphones again. And welcome to the office hours section of the stream. Let's go ahead and see what's on our agenda for today. I mean, I already explained it for those who showed up for the earlier part of the stream, but we are continuing with the topic of Riemann sums from last week. So I did figure out why this did not come out to what I was expecting it to be. I was expecting to get 1/3 b cubed minus a cubed, but the reason I didn't get that is because let's see, which page was it on? Was it on this page? Yeah, it was because I plugged in a equals 0 and I eliminated those two terms. So if those two terms had been included, then that would have added enough stuff in here to then cancel a bunch of the things that I get from foiling b minus a cubed. And that would have resulted in 1/3 b cubed minus 1/3 a cubed, which I think I'm going to go ahead and do because we might as well. It doesn't hurt. Maybe it'll help with checking my work too and make sure that my work from before was done correctly. So let's see. If I add these terms back in, then, well, we already took care of this term last time. This term, when we took the limit of it as n approaches infinity, we ended up with this thing, which was b minus a all cubed over 6 times the limit as n approaches infinity of 2 plus 3 over n plus 1 over n squared. The 3 over n and 1 over n squared went to 0, and that just multiplied the 2 into our 6, reducing it to a 3. The 2 into our 1 over 6, reducing it to 1 over 3. So yeah, that third sum is already taken care of. Let's take a look at these other two sums. So limit as n approaches infinity, let's see. Limit as n approaches infinity, I'll do one term at a time, of, what was it again, a squared delta x? Yeah, a squared delta x times the sum from I equals 1 to n, yeah, from I equals 1 to n of 1. Well, what is this sum over here? I would do 1 plus 1 plus 1 plus 1 plus 1, how many times? Up until I've added 1 n times. So n ones would add up to a total of n. So this simply becomes limit as n approaches infinity of a squared times our delta x was what again? It was b minus a over n, right? Delta x was b minus a over n. Just double checking and making sure I didn't define it differently anywhere here. Yeah, delta x is b minus a over n. Limit as n approaches infinity of a squared times b minus a over n times this sum just becomes an n. Well, these n's cancel out. And so I'm left with a squared times b minus a, which is independent of n, so this just becomes a squared b minus a squared a, which is a cubed. Okay, so that's our first term taken care of. Now for our second term, 2a delta x squared times the sum from 1 to n of I. Our next term is limit as n approaches infinity of, I've already forgotten, 2a delta x squared? Yeah, 2a delta x squared, sum from 1 to n of I. Well, we talked about this sum before. If you just add the numbers, first I equals 1, then it's 2, then it's 3, 1 plus 2 plus 3 plus 4. We talked about that last time. We said that this sum is just equal to n plus 1 times n all over 2. So we can go ahead and make that substitution and also substitute the delta x while we're at it. So we get limit as n approaches infinity of 2a, and then delta x squared is going to be b minus a quantity squared over n squared times, that sum becomes n times n plus 1 all over 2, right? Did I copy that correctly? N plus 1 times n over 2, same thing. Okay, one of the n's cancels out there. The 2, this 2, cancels out with that 2. And then n plus 1 over n. Well, I can factor out the a and the b minus a squared, so a times b minus a squared can be factored out of the limit since they don't depend on n. And I see the sniffles are coming back from before. Sorry about that. I hope that doesn't get too annoying. And we've got, what's left inside? N plus 1 and n in the denominator. So n plus 1 over n. That's going to be n over n, which is 1, plus 1 over n. N plus 1 over n reduces to n over n plus 1 over n. And 1 over n, as n goes to infinity, 1 over n goes to 0. So this limit just becomes a 1, which means we're just left with a times b minus a squared. Okay, now we have all the pieces we need, and those sums were all just, added to each other. So let's go ahead and add these terms to that term and see what we end up with. It should be 1/3 of b cubed minus 1/3 of a cubed. Oh my goodness. Out of all the times that my nose decided to act up. Okay, hopefully that'll do it. Okay, so we had 1/3 b minus a cubed. Well, let me write them in order. So this term was first. So if I had done this without dropping those two terms at first, I would have had them as a squared b minus a cubed plus this a b minus a squared, which I will expand in a minute, plus this 1/3 of b minus a all cubed. Let's see what we can do with this. So that doesn't need any more simplifying. This becomes a times, let's see, b squared minus 2ab plus a squared. So that's a times b squared minus 2ab plus, whoops, a squared. Not b squared again. That would have been a fatal mistake right there. Okay, plus 1/3. Let's copy that over. A squared b minus a cubed. Okay, b minus a all cubed. I'm going to start with b minus a squared and then multiply it by b minus a. What was it? It was 1331, but I don't want to take shortcuts here. I'd rather do it slowly and carefully, especially since some people might not know that shortcut. So I'm going to do b squared minus 2ab plus a squared, that's just b minus a squared, times, we've got one more b minus a. And if we multiply the b minus a into this, first of all, is there anything that cancels among these terms? I would hope so. That can reduce the amount of writing I have to do here. I see a minus a cubed, and if I distribute this a, I'm going to get a plus a cubed over there, so plus a cubed and minus a cubed, those will cancel out. A squared b, well, when I multiply the a into here, I'll get minus 2a squared b, but other than that, not much. Let's see. A squared, let's see, a squared b. I'll write the ab squared, actually, yeah, I'll write the ab squared first. So ab squared from here. And then minus 2a squared b plus 1a squared b. Minus 2 and plus 1 is minus 1a squared b. And that's all that's left of those two terms, it looks like. Plus 1/3 of, here we go, b times all this stuff, so that's going to be b cubed minus 2ab squared plus a squared b and then minus a times b squared, so minus ab squared, and then minus a times minus 2ab is plus 2a squared b, and then plus a squared times minus a would be minus a cubed. Did I do all that right? So distributing b, I get b cubed minus 2ab squared and plus a squared b. Distribute minus a and I get minus ab squared plus 2a squared b and minus a cubed. Okay, that is all looking good. Is there anything in here that cancels out? Well, I have like terms that combine. I've got a squared b combines with 2a squared b to make 3a squared b. So I've got 3a squared b, and I've also got minus 3ab squared. So I've got, copy those over, a b squared minus a squared b plus 1/3. I've got the b cubed, and I'm going to go ahead and write the minus a cubed. And then for these in-between terms, I've got minus 3 ab squared and plus 3 a squared b. And if I multiply each of those by the 1/3, if I distribute the 1/3 to them, then I get minus ab squared over here, which cancels out with the plus ab squared. This ab squared cancels out with minus 3ab squared divided by 3. And similarly, 1/3 of 3a squared b minus the a squared b on the outside, those also cancel out. And I do indeed end up with 1/3 of b cubed minus a cubed. Okay, perfect. That is what we are supposed to get. And of course, if you plug in b equals 3 and a equals 0, we still end up with 9. But now that we have it in this format, now that we have it in the proper format, it will work even for cases where a is not 0. So this over here, this 1/3 b cubed minus a cubed, this can be represented as the original function we started with was the function f of x equals x squared. And we were calculating the area under its curve from 0 to 3, from a equals 0 to b equals 3. So we represent this in calculus as the integral from a to b of the function x squared integrated with respect to x. Integrated with respect to x. And did I actually show that last time? Yeah, I did that over here. So this dx, we know the variable we're integrating with respect to is the variable for which we take really small deltas, or, well, in this case we had pretty big deltas that became really small when we took the limit where n approaches infinity. But yeah, those really small deltas basically turn into this dx in the integral form of this sum, and the integration bounds, the interval over which you're calculating the area, become the bounds of this integral. And then inside of that you have this function. So official terminology, this dx thing is called a differential. That dx is called a differential. It tells you what your variable of integration is. The function that goes inside of the integral is called the integrand. Which might not be too foreign to you if you know, for example, that the numbers in a multiplication are called multiplicands, or the number being divided in a division problem is called the dividend. It's that kind of terminology that we're looking at. So when setting up integrals, the thing that you need to remember is that the variable of your integrand must agree with the variable indicated by your differential. Otherwise, you can't really do anything. I won't go over a proof of this rule, but the basic idea for at least polynomial functions is that to do their integrals, all you have to do is increase the exponent by 1, so x squared becomes x cubed, and then you divide by whatever that new exponent is after you've done that increase. So if the 2 becomes a 3, we then divide by a 3, and you get x cubed over 3. Then what you do is you substitute the upper bound and the lower bound, and you calculate the difference between those two. So let me actually write that out on a new sheet of paper. Let's go ahead and write that out on a new sheet of paper. Integral from a to b of x squared, getting ahead of myself, with respect to x, is equal to, we would call this x cubed over 3 from a to b. This basically means we take this x cubed over 3, we plug in b first, so it becomes b cubed over 3, minus, and then we take this expression again, but now we plug in the lower bound for x. And there you go. That's the basic idea of how to deal with these integration bounds. When an integration has bounds, it is called a definite integral. So this is an example of a definite integral. When an integral doesn't have bounds, that's called an indefinite integral. It has multiple possibilities for what it could be, because you're basically doing the opposite of a derivative, except a derivative is a one-way process, while the integral is not a one-way process, because there's more than one function that has the same derivative. If that doesn't really make sense to you because you haven't had any calculus yet, you might want to look at that stuff first, but you don't really need it for what we're going to do today. I'm just, providing some extra information here. So I guess what I want to do now is just give you a general formula for the integrals of polynomial functions. If I'm doing an integral of a polynomial function, I'm not going to write bounds this time. If I am going to find bounds my brain is thinking faster than I can talk. Let me slow down. I want to write the general formula for the integral of a polynomial, or at least a polynomial term. So if I have x to the n, if I'm taking the integral of x to the n with respect to x, then the formula for that is, as I described earlier, you increase the exponent by 1, and you then divide by that new exponent. So the new exponent is n plus 1, I divide by n plus 1. And then this is something from calculus class. You also have to add a constant here, because the idea is that this is the reverse of a derivative. The idea is that this is the reverse of taking the derivative of a function. And if you take the derivative of a function, again, sorry if this sounds foreign to you, but for the people who know derivatives, you might want to pay attention to this. If I did something like the derivative of x squared plus 5, and I also did the derivative of x squared minus 12, and I did the derivative of x squared plus 107, and I did the derivative of x squared minus 382. All of these functions will have the same derivative. All of them will have a derivative of 2x. All of them will have a derivative of 2x. So if I want to undo that derivative, then let's see, x to the first power becomes x to the second power, so 2x to the second power, and I divide by that new exponent, 2, and so those 2's cancel out. So I've got back my x squared, but I also have to put in this plus c here, and I don't know what this c is. It could be 5, it could be negative 12, it could be 107, it could be negative 382. There's multiple functions that have the same derivative, so when I reverse the process, I have to pay respect to the fact that I have multiple possibilities for what this function could actually be, and I would need further information to determine the actual value of this c. For the students who haven't done derivatives, don't worry too much about this. Just know that this is something you need to include when you don't have integration bounds. Technically, you could still include it if you have integration bounds, except the problem is it just disappears. If I were to go back here, for example, if I were to go back here, and instead of x cubed over 3, I did x cubed over 3 plus c. If I did x cubed over 3 plus some constant evaluated from a to b, then what that would mean is I would take b cubed over 3 plus whatever that constant is, minus a cubed over 3 plus whatever that constant is. The constant cancels out. So when you have a definite integral, when you have an integral with clear integration bounds, you do not need the constant of integration. It just cancels out. But if you have an unbounded integral, if you don't know what your integration bounds are going to be ahead of time and you're just trying to derive a general function, you need more information. Otherwise, you have to put your ignorance on display by including that plus c. And I mean put your ignorance on display in the literal sense, not in some sort of I don't mean it in the sense of like embarrassing yourself. I mean just being honest about the fact that you do not know. Anyway, we're not going to worry about that too much. Instead, we are going to now try and apply Riemann sums to something more than just what we did last time, which was rectangles. There are other sorts of things that we can chop things into. So let's do the derivation of the volume formula for a cone. Volume of a cone. Let's see if we can make sense of the volume of a cone. So let's draw a cone. Looks something like this, and then has a circular base. It goes something like that, right? It's going to have some sort of height. I'm going to call that capital H. I will not specify what this height is, but it is a constant. That's the key thing to remember. Whatever this height is, sure, it's unknown, but it's also a constant, not a variable. Just because something is unknown doesn't mean that it's automatically a variable. Similarly, I want to define the radius of the base of this cone as capital R. Again, a constant. I'm trying to derive the general formula for the volume of a cone, which, regardless of its base radius and height, will always be, as we were taught in geometry, volume equals 1/3 pi radius squared times the full height of the cone. That's the formula we were given, but we were never taught where this formula even comes from. Well, today is the day that we try and prove this formula. Today is the day. Let's grab the orange pen for this. So, similar to how I calculated the area under the curve of x squared by chopping the area into smaller, more manageable pieces, namely rectangles, I want to do the same thing with a cone. I want to take a cone and chop it into pieces that are simpler to deal with. What is a simpler shape that I could chop a cone into that approximates the volume of a cone? What would that be? Well, if I chop it horizontally into its cross sections, then I end up with something not too different from a stack of discs that have successively smaller and smaller radii as I progress to the top. And I think I actually want to draw the top first. Yeah, something like that. And then next disk will be something like that. I know I'm taking my sweet time with this, but I think it's worth it. And maybe, yeah, one more. If I were to take a stack of these, what would I call them? Really short cylinders. We refer to them as disks, but they're also cylinders. If I were to take a stack of these disks and calculate the volume of each individual disk and add them up, they do approximately look like they would add up to the volume of this cone, especially if the combined height of the disks was equal to this capital H, and if the radius of at least the lowest disk is still capital R. This looks like it might give me a somewhat decent approximation of the volume of a cone if I added up the volume of these little disks. So what if I sliced these disks thinner and thinner and thinner, and I just stuffed as many disks as I could? Like if I stuffed more disks between the ones I've already drawn, and then even more disks between those disks, and so on and so forth. If I just did this as much as possible, if I tried to get a near infinite number of disks, making them practically razor thin, then you could argue by the same logic that we used over here for rectangles. The thinner we made the rectangles, the better the approximation of the area became. Well, the thinner the disks are, the better their total volume approximates the volume of a cylinder. So let's see if we can come up with some sort of relationship that determines the volume of an individual disk. So each individual disk is going to have a small piece of the total volume. Each of these disks is going to have a small piece of the total volume of this cone that we're trying to figure out. The volume of a disk. The volume of a disk is going to be, let me draw like a zoomed in picture of one of these many disks. This disk is going to have a radius little r. I'm not going to call it big R because only the bottom disk is going to have a radius of big R. All the other disks are going to have radii between big R, and then I guess the topmost disk will have a radius of basically 0 to represent the tip of your cone. So I'm going to use little r for the radius of any random disk within this stack. It's going to have some sort of height that's going to be a segment of this total height. I'm going to call this delta H in a similar manner to how I used delta X for the widths of my rectangles that spanned some larger interval along the x-axis. Here, I'm going to give each disk the same height, the same delta H. And I'm going to make the disks so thin that these delta H's become negligible, in much the same way that I had my delta X's for rectangles become negligible by just creating more and more rectangles. So if I know these two things, then the volume of any given disk is going to be the area of the base, pi r squared, it's just a cylinder, times the height, which I'm going to call delta H. So the volume of an individual disk is going to be pi r squared times delta H. Where do we want to go from here? Well, we need to define an interval over which we are stacking our disks. We need to define an interval over which we are stacking our disks, and a good way to do that is to draw our cone sideways and superimpose it, that is, lay it against a coordinate system. So let's do this. Let's do a side view of the cone. And a side view of the cone is going to look like this. So this is a side view of the cone. It's going to have this distance be equivalent to the height of the cone. So I guess our delta H's would be just little sections of this horizontal axis. And then any random distance from this axis to a point directly above it or below it, that would be a radius. That would be the equivalent of the radius at that point. Okay, so it looks like our H variable is going to be from the value of 0 to the value of capital H. It looks like we are working from, it looks like our H goes from 0 to capital H. We could also think of it in another way. We could think about it in terms of radius. So let me see, do I actually want to rotate this? I suppose I could do that. Yeah, if we were to rotate this view 90 degrees, so if I were to draw another coordinate system, another way we can think about this, I did it wrong. I'm supposed to make this one longer. Another way we can think about it is we can look at the cone, again, sideways, but I'm going to look at it, I guess I'll look at it upside down. We could also think about it as the radius being on an interval. That should be symmetric, but I drew it poorly, where the radius starts at 0 and goes to a maximum of capital R over here. We could also think of our radius as existing on an interval from 0 to big R. You can actually solve this one in two different ways, depending on which of these perspectives you want to take. I want to take the perspective that we are actually going to be stacking these from a radius of 0 to a radius of big R. I think that might be the better way to go about it. Well, I'll think about it some more. Let's just keep moving with this formula, and then we'll decide whether we want to define our bounds in terms of H's or in terms of R's. Let me see. So the volume of an individual disk is equal to pi r squared times delta H. if I were to my mind is drawing a blank. I even rehearsed this. Man, after all that prep time. Like, I know the outcome that I'm supposed to get, but what I'm struggling with right now is how to explain it in terms that are easy to digest for somebody who's learning it for the first time. Yeah, I'm not sure. Let me just proceed with this. So let's pick out a random disk from this sort of side view that I drew over here. And I guess we'll pick out this as our random disk of choice. There's going to be some sort of delta H associated with it. We're going to multiply that delta H by pi and whatever this radius is squared. And I want to come up with a relationship between R and H. I want to come up with some sort of relationship between R and H that will help me determine how R changes with H or vice versa. So what I can do is I can just draw similar triangles, or similar cones, if you will. I will do that over here. So let's say I draw two cones, two triangles, however you want to think about it. Let's say I draw a second cone over here. And this second cone, its base is going to have some radius r, while the main cone has a radius of big R. This little cone is going to have a height I'm going to call little h, while the full height of the cone is big H. And if you remember your geometry, you remember that similar figures have equal proportions between their dimensions. That wording is probably confusing, but you can probably intuit that little h over big H is the same ratio as little r over big R. Little h over big H is equal to little r, is equal to little r over big R. And we need this. We need this because otherwise we're going to run into a problem. So when I want to figure out the total volume of this cone, if I want to approximate the volume of the cone using these disks, then I want to calculate the sum of a bunch of pi r squared delta h terms. I would want to express either the h in terms of r or the r in terms of h, because when I turn this into an integral, it's going to become the integral of, I guess, our delta h is going to become a dh over here, and this is going to become the integral of pi r squared dh. This is hinting back at what I was saying earlier about the integrand and the differential. Where was it? Right here. Your integrand and differential need to agree with each other. I cannot do this integral as it is right now because my variable r is not defined in terms of h. So I either need to change this differential or I need to change this variable. We haven't really learned how to change differentials, so I'm going to focus on changing the variable. Fortunately, we've got this, so we can redefine r as, let's see, I'll do it over here. Just multiply the big R over to the left, and you've got little r is equal to big R over big H times little h. Okay, and now we can substitute that in for our r, and that gives us the integral of pi big R over h times little h dh. Okay, I guess we have to define our integration bounds now. Since we are integrating with respect to h, our integration bounds should be in terms of h. So I guess we are integrating from h equals 0 to h equals big H. So our integration bounds are going to be from 0 to big H. Now, the pi, the big R, and the big H, those are all constants, and they're not really going to affect our integral. They're not really going to affect our integral. We can factor them out. They are independent of our variable little h, so they can just be factored out of the integral. Kind of like if you were to imagine, if I were to go back to this graph of x squared, and instead it was a graph of 2x squared or 3x squared, some constant times x squared, then all that would do is it would multiply the heights of all the points by whatever that constant is. So if it was 3x squared, each of these rectangles would be 3 times as tall, but they would still have the same width, so they would end up having just 3 times the area. 3 times the height with same width would give you 3 times the area. So multiplying your function by a constant has the effect of just multiplying the end result by that same constant. That's all it really does, so I can factor it out of the integral and save it for later. I can factor out pi big R over big H, and now all I have to do is the integral of little h with respect to h. Okay, so this is just a polynomial function. It's h to the first power. I can just follow this formula. By the way, this is called the power rule of integration. I can just follow the power rule and say, when integrated, this h becomes h to the 1 becomes h to the 2 divided by that new 2. So it's going to give me, let's switch colors, and I don't even think I can fit it all in here. I might have to write it on another page. I'm left with pi big R over h times h becomes h squared over 2, and that is going to be evaluated from 0 to big H. Equals pi big R over big H times, I guess it'll just be big H squared over 2. Hold on, did I do something wrong? I did do something wrong. I'm seeing it now. Okay, I screwed something up. I forgot to square my R. I forgot to square my R. This big R over big H times H needs to be squared. Okay, let's do that on the back side. Let's start that over. So we had integral from 0 to big H of, we had pi r squared dh. R squared becomes big R over big H times H all squared dH. Did I copy that correctly? Big R over big H times H. Yep. Okay, now this becomes, I'll factor out the pi, and that becomes big R squared over big H squared times little h squared dh. I'll factor out the big R squared and the big H squared. Pi big R squared over big H squared times the integral from 0 to h of h squared dh. Okay, now we're back on track. This is going to become h cubed, and then we're going to divide by 3. So that's going to be pi r squared over h squared equals h cubed over 3 evaluated from 0 to big H equals pi big R squared over H squared times big H cubed over 3 minus 0 cubed over 3. Well, the 0 doesn't add anything, so we're just left with this big H cubed. H cubed reduces with H squared to just an H, and all that's left is pi big R squared big H over 3. Or 1/3 pi r squared h. That is the volume formula for a cone. Now we could do a thing where we change the variable of integration. We could change this dh into a dr, and that actually still uses this over here. We could do that, but I don't want to introduce that idea to students who may not have done the U substitution rule, because it's going to look very foreign, and I'm not sure how I would properly explain it to someone who hasn't had that calculus experience yet. But there you go, that's the volume of a cone through stacking the volumes of a bunch of disks. I skipped the phase where we actually set up an approximation. I just kind of wrote an incomplete summation over here and just basically implied that it leads to this, it implies this. And I hope you can see that from, I think I showed it last time, did I not? Where was it? I know I had something around here somewhere. Where was it? I could have sworn. Wait a minute. Where is it? Oh, there it is. Yeah, I even pointed to it earlier today. Yeah, your sum basically takes your, if you're calculating a sum where you've got a function times some sort of delta, your delta eventually turns into this differential, and the function that you're summing just becomes the integrand. It is kind of hand-wavy logic, but without teaching you a full calculus course, I think that's the best I can give you for now. So how about we move on to something else? How about we try and apply the idea of Riemann sums to something else? How about a problem that we run into in physics sometimes, where you might have an object with a variable density. Let's say, for example, that we have, let's say we have a sphere. Let's say we have a sphere. And let's say this sphere has a total radius of big R. And let's say that the mass of this sphere is not distributed evenly. Let's say that the mass of this sphere is not distributed evenly. What if we had a sphere where it had no mass at the center and its outer shell was the densest part of it? So it's the least dense at its center, and it gets heavier and heavier and heavier as you go outward. How would I describe the mass of this object? Let's say that the density varies linearly as you move out of the radius. So sphere with density that varies linearly. Probably not the most useful example for mechanics, but for electricity and magnetism you might see something like this. It would be a charge density rather than a mass density in that case. But yeah, a sphere with density that varies linearly with increasing, that varies linearly with R, that varies linearly with radius. I would describe this as having something called a density function. I would say density, in this case, the symbol for density we're going to use is the Greek letter rho. That's what's commonly used in physics. Rho, as a function of R, is equal to, let's see, if it varies linearly with R, then I'm just going to say it's a constant. Let's call that constant K, times R. Seems simple enough. When R is equal to 0, density is 0, so there's no mass at the center. When R is equal to, I don't know, 2, then it's whatever this K is times 2. Okay, let's find an expression for the total mass of this object. So let's find an expression for the total mass of this object. M, total mass. What would it be? In case you've never really worked with density before, in case you haven't had chemistry, or physics 2 would be the other place you encounter the concept of density, let's do a quick briefing on what density is. So, for a lot of objects in the world, you're going to see they're just made of one solid material, and their density is just evenly distributed throughout the volume or area or length of that object. If I have, for example, this ruler, I would assume if I chop it up into pieces that are 1 inch long, I would assume each piece weighs the same. I would assume each piece has the same amount of grams per inch of whatever this material is. If I had like a block of wood and I sawed it and diced it into little pieces, I would expect equally sized pieces to have equal masses. That's what we call a uniform density. That would be when the density is just equal to a constant. That's not what we have here. Here we've got a variable density. But the way that it's used to calculate mass is still the same. The density of a piece of an object can be multiplied. The density, in this case the mass density, is simply the mass per, and then here insert whatever you like, mass per, when it makes sense, mass per length, like the example of my ruler. When it makes sense, mass per volume, like my example of the wood block, or sometimes even per surface area, Sometimes, for example, this piece of paper, if I were to chop it into little pieces, squares, triangles, whatever, I would expect pieces of equal area to have equal amounts of mass to them. And if I wanted to figure out the mass of a couple pieces of paper, what I would do is I would calculate the mass per area and then multiply it by the total area of whatever piece I'm holding to figure out the mass of that particular piece. Same idea with length and volume. If I cut off a random piece of this ruler and I wanted to figure out how much it weighed without actually, weighing it on a scale, I could just measure its length, and if I knew ahead of time how much mass existed per length, then I would take that mass per length multiplied by the length to get the density. So in this case, we have a density in terms of mass per volume, so I want to multiply it by volume. So mass per volume times volume equals the mass of an individual piece, equals mass of an individual piece or section of the overall thing. Mass times volume, or not mass times volume, density. Mass density times volume, in this case, would give me the mass of a particular piece. Assuming, of course, that your density was constant. Here, our density is not constant, but we can make it constant if we just minimize the change in r. If we have very little change in distance from the center, then over that very small change, the density will be approximately constant. We can do that. We can slice this cylinder into pieces, or not cylinder, sphere, into pieces. These pieces will be cylindrical shells, which I'm not really the best at drawing, but I'll try my best over here. So let's see. If I were to take this sphere and cut it up into a bunch of nested shells, I'm not sure how I'm going to make this look 3D. Maybe we'll just have to settle for looking at a cross section. If I were to chop this sphere into a bunch of little spherical shells, how am I going to make this feel 3D? I don't know, I feel like I've already messed it up. Yeah, I'm not sure. Maybe if I draw some sort of okay, let's say that we've chopped a sphere in half and we're looking at the inside of it like this. Yeah, and then this is kind of like a dome in the back. Okay, so we're looking at just one half of our sphere and we're looking inside of it and we're seeing all these kinds of rings, all of these half spherical shells. That's basically what I'm trying to chop this thing into. If I make these shells super thin, then the difference in R from, let's use a different color, then the difference in R from here to here, you've got a different radius here versus here. If I make these shells really, really thin, then the change in R will be so small that the change in density between the inner part and the outer part of this one shell will also be negligible. I will be able to treat my density as if it's being constant, kind of the same way as, again, I'm going to keep referring to this image, as if I'm treating the height of this curve as being just equal to this height of the rectangle for the whole interval. As long as I shorten my interval, that approximation will just get more and more accurate as I go. So yeah, for an individual shell, for any individual one of these shells, I can treat the density as being constant for that particular shell. Then I can say that the mass of an individual shell is equal to the density, which will be constant for that shell, or constant enough, times the volume of that particular shell, times the volume of that particular shell. Okay, density, we can just rewrite it as Kr. So the mass of an individual shell is going to be Kr times the volume of an individual shell. Well, these shells don't all have the same volume, so I'm going to have to either write my radius variable in terms of volume or write my volume variable in terms of radius. Writing my volume variable in terms of radius is probably the better way to go. So what would be the volume of an individual one of these shells? Let me try and draw one. Let me attempt to draw one of these shells. Let's see, and I'll draw a half shell rather, since that seems to be the best I can do. I'll draw a half shell like this. So I'm just looking at one half of a shell. It's going to have a radius, some random radius, little r. It's going to have some random radius, little r. It's going to have a difference between its inner and outer radius, which is going to be relatively small. We'll make it small the thinner that our shells become, but this difference between the inner and outer radius, I'm just going to do this, two arrows just kind of pinching it. This I'm going to call my delta r. And what I can do to calculate the volume of this shell is I can calculate the surface area of a sphere. I know the surface area formula for a sphere. I would hope that you recognize this. Surface area of a sphere is equal to 4 pi times the radius squared. I would hope this equation looks familiar to you. If not, then you might want to look through your geometry book if you still have it, or I guess there's always Google. The surface area of a sphere is 4 pi r squared. If I take the surface area of a sphere and multiply it by its thickness, that should give me the volume of a shell, or at least the approximate volume. This is kind of the same logic as if I take a brick or maybe not a brick, but like a thin tile of whatever shape. It doesn't even have to be rectangular. And I take the area of that tile's base and multiply it by whatever little thickness it has, this thickness. That would give me the volume of that piece. Kind of the same thing is going on with this spherical shell. This was probably not the best example to start with in hindsight, but we're committed, so let's go through it, and maybe I'll give another example that will hopefully be much simpler than a sphere. I have attempted to give examples with spheres twice this week, and both times it has failed me. I should probably not be looking at spheres for a while until I've prepared a more digestible explanation for how to work with them. Okay. Anyway, thickness multiplied by surface area equals volume for a thin spherical shell. Yes, the curvature kind of adds a twist to it, but remember, we're making these things so thin, we're making this delta R so small that that's not really going to matter. So I guess I'm asking you to rely on your intuition to a great degree today in order to convince yourself that what I'm doing makes sense. I don't have the most rigorous proof for what I'm doing today, unfortunately. I've always kind of just done it intuitively myself, and I've never really had to teach this before, so I guess I'm learning stuff here too. Surface area of a sphere, 4 pi r squared multiplied by the thickness, volume of a shell, volume of thin shell, is going to be 4 pi r squared times this thickness delta r. Okay, now that I have the volume of a thin shell, I can put it in here. Mass of an individual shell is kr times volume of a shell is 4 pi r squared delta r. And if I want to do this for multiple shells, if I want the total mass equals the sum of the masses of shells I, where I starts from whatever your first shell is, I guess it would be shell 0 up to shell n. It would be the sum from I equals 0 to n of, let's multiply the k and r into this, and that would give us 4 pi k r cubed delta r. And then if I took the limit as n approaches infinity of this sum, then I would end up getting the integral. I would end up getting the integral from the first shell of radius, I guess 0 would be the innermost shell, to the outermost shell, which would be at radius of big R, the full radius of the sphere, times 4 pi k r cubed, and then my delta r would just become a dr. Okay, the 4 pi k, those are constants. I can just factor them out of the integral the same way I can factor them out of this summation. And I'd be left with 4 pi k integral from 0 to big R of r cubed dr. R cubed dr, that will integrate to, well, a cube becomes a fourth power, and then we divide by 4, so that becomes r to the 4 over 4. 4 pi k times r to the 4th over 4, evaluated from 0 to big R. Technically, you can skip this step and just skip ahead to big R to the 4th minus 0 to the 4th, but I'm writing these steps in between just because this is probably new to a lot of people. 4 pi k times, that's just going to be big R to the 4th over 4 minus 0 to the 4th over 4. I probably should not have written all this stuff so close to each other. Let me see if I can use a different color to, yeah, that should make it a little bit more readable. There we go. And then, yeah, 0 to the 4 over 4, that's just gone. And this 4 cancels with this 4, and I get the total mass is equal to pi k times the radius of the sphere to the 4th power. Okay, not really the best example I could have given, but maybe this is something to revisit later once you've had more experience and it'll make sense at a later time. I do not blame you for being confused by this. Let's do, I guess one that would be relevant to physics mechanics would be moment of inertia. And let's do moment of inertia for, how about moment of inertia for a uniform cylinder? Do I have, the back of that is already covered, so new sheet. Let's calculate the moment of inertia. Let's calculate the moment of inertia for a uniform cylinder or disk. A disk is just a really short cylinder, so they're basically the same thing. Those who may have taken Physics 1 before and are now doing Physics C might have seen this formula in textbooks. You didn't have to memorize it, but moment of inertia for a cylinder or disk was equal to 1/2 times the total mass of the cylinder times the full radius of the cylinder squared. In general, moment of inertia for a mass, for a point mass, is equal to whatever that mass is times its distance from the axis of rotation squared. And for those who haven't done any physics before, this is probably not making any sense, so let's explain this idea. So suppose I have a cylinder over here, and my axis of rotation is running through its center. That's also something I should have specified here. Cylinder or disk with rotation axis through center, Specifying the rotation axis is important. Through the center. And I suppose that's not even the best description, because through the center could also mean, like, this way, but I think my drawing already sufficiently illustrates which rotation axis I'm talking about. I'm talking about this. So a moment of inertia, for those who don't know their physics, basically it's the resistance that an object has to rotation. If I try to rotate something, like if I try to rotate this ruler, if I try to twirl it by holding it from the middle, I don't have much difficulty doing that. It's pretty easy to twirl when I hold it from the middle. It's pretty easy to make it rotate clockwise or counterclockwise. I don't require that much effort. However, if I try to rotate it from its end like this, then I have a much harder time. It would be easier if I used a more rigid ruler, but I don't have that, so I have this rubber ruler that kind of flops. But if you have some sort of rigid stick-like object, try twirling it through its center versus trying to rotate it by holding it from an end, or not even from its end. You could just twirl it. You could try to twirl it from somewhere off center, and it will feel harder than rotating it from the center. And that's what moment of inertia is about. What I'm doing by changing the position that I'm rotating it from is I'm changing this axis of rotation. Basically where my thumb is the axis of rotation that I'm using, and different axes of rotation will allow you to encounter different resistances to that rotation. The most resistance to rotation is encountered when more of the mass is farther from your axis of rotation. So the more mass you have, that I think is intuitive enough, the heavier it is, the harder it'll be to twirl it. But also, where you position your axis will determine this, which is usually the biggest factor. This R thing is the distance from the axis. If I put my axis of rotation in the center, what that means is that the farthest parts of my ruler, the farthest parts of this ruler's mass, are at the minimum possible distance they could be. Because if I grab the ruler from further, like here, then the mass at this end of the ruler is, what is this? Let me see. I'm holding at 7 centimeters, and that's at approximately 30. So right now, the farthest parts of this ruler's mass are 23 centimeters, 23 centimeters away from my axis of rotation. Whereas if I hold it from the middle, the farthest pieces are only 15 centimeters away. So yeah, if I minimize the distance of the farthest parts of an object, that will usually reduce the amount of effort I have to put in to twirl and rotate that object. So that's what moment of inertia is for those who haven't learned the physics yet. So for a point mass, if this ruler, actually, you know what, forget the ruler. Let me grab a dumbbell. I don't even know if this thing is going to show up on the screen properly. I don't know if it will completely fit, but look at this dumbbell. Yeah, that doesn't fit completely on the screen. Oh well, we'll work with it. Is that better? I suppose. So with this dumbbell, you've got a smaller part of the mass is over here in the middle, and most of this mass is going to be really close to the axis of rotation if I try to rotate it, from the center of the actual bar part of it. But then you've got these two different lumps of mass that are pretty much entirely, let me see, what does my ruler say? How long is this thing? This thing is this central bar is about 15 centimeters long. So yeah, I've got these two little lumps of mass that are 15 centimeters away from this axis of rotation. So if I treated the masses of these two lumps as being at a single point, I would say that the mass is at a point that's, let's see, if this was 15 centimeters, then I would say, and let's pretend that the mass of this central part is mostly in these two lumps as well, then I would say, what is this? Is this a 15-pound? Yeah, this is a 15-pound dumbbell. So I would say that half of my 15 pounds, so I would have a mass of, let's see, it would be 7.5 pounds divided by whatever G is supposed to be in imperial units. That would be the mass of one of those two lumps. I would multiply that by, what was the distance? It was 7.5 centimeters. I would have to convert that to correct units as well. And then I'd have to square that. And then that would be the moment of inertia for one lump, for one point of mass. And then I would also have to add the second lump. So in this case, I would have to just multiply by 2. But in general, the moment of inertia for a rigid object that contains its mass at more than just one point. The moment of inertia for a rigid object is actually the sum of each little bit of the object's mass times the distance of each bit squared from the axis of rotation. And you would just have to sum those up. But this is the base formula that we would start with. Let me put this dumbbell away. I didn't mean to turn this into a physics lesson, but I imagine a lot of physics students will be interested in this topic anyway, so perhaps that's a good thing. Wait, don't want to use this color. I've already used it enough. Let's see. So, what was I trying to say here? So yeah, basically, I'm trying to work with this. I want to chop this cylinder up into a bunch of little pieces, and I want to do that in such a way that I guess the most critical variable here would be r, this r thing. I want this to be approximately constant from piece to piece. And the ideal way to chop this up then would be not too different from what we did with the sphere, actually. I want to cut this cylinder up into a bunch of cylindrical shells. This is going to work very beautifully for us because of rotational symmetry. If I chop my cylinder up into a bunch of cylindrical shells, this is going to work really nicely because if I make my cylindrical shells thin enough, then their radius will be approximately constant, and that would mean that all points within an individual shell will be the same distance away. So then the moment of inertia for a particular shell is just going to be the mass of that shell times the radius of that shell squared, And then if I just do this for each and every shell and I add them up, there you go, I would get the moment of inertia for the whole cylinder, or at least an approximation for it, unless I take an infinite number of these shells and make them really razor thin. Okay, so that's great and all, but how do I know how much mass is contained within a shell? We said that this is a uniform cylinder, so the mass is distributed evenly per volume. So the outer shells are going to be obviously bigger than the inner shells, and when an object is uniform, the bigger its pieces, the more mass those pieces contain. So I need to come up with a formula to figure out the mass of an individual shell based on its size. And for that, I need to actually figure out what the size of a shell is. So let's take one of these cylindrical shells. I did this before, I think like 4.5 years ago in one of my AP Calculus review videos. If we take one of these cylindrical shells, say you take like an empty roll of toilet paper and you grab some scissors and you cut this thing open and you unfurl it. Let's say I take some scissors and I cut this thing open and I unfurl it, and I'm going to lay it sideways. So I begin to unfurl it, Maybe first it looks like this when I first open it up. And then I guess I would have to, let's see, draw something like that. I think I messed up this drawing really badly already. Yeah, I think I've already messed this up. Okay, actually no, I think I've saved it. Let's say I start unfurling this thing, opening it up, and then so, I don't know, cut it along this line, cut it along this dotted line with some scissors, and then start opening it up. Eventually, you unwrap it, and it ends up looking something like this. Okay, I think I messed up that part. Yeah, I feel like I'm missing a line somewhere in the front of this thing. Just goes to show how important art skills are for teaching. But yeah, if you unfurl this thing and you open it up, you can make it kind of flat. It'll still have a little bit of curvature to it because the thickness is not negligible. You'd probably have the easiest time doing this with something as thin as the cardboard of like an empty toilet paper roll. I think that would be the best example that you can play around with at home. But yeah, take some sort of cylindrical tube thing, cut it open from the side, and unfurl it, and you can mostly flatten it until it ends up looking approximately like a square or rectangular tile. Until it ends up approximately looking like some sort of square or rectangular tile. Okay, what's the volume of this thing? Well, this would be just the area of its base times whatever this is, whatever this height is. That would be its volume. So for the area, I would just take whatever this length is, L, and multiply it by whatever this width is, W, and yeah, length times width times height. If you make your cylinders thin enough, then there's little difference between this curved shape that's not quite a rectangular prism and this thing, which is a rectangular prism. When you're dealing with really, really thin shells, the difference just disappears. So let's figure out what these length, width, and height are. Well, the height is just going to come from here. Whatever the original thickness was of the cylinder before I unfurled it, that would be this, which becomes this, which becomes this. There you go, that's the height. Okay, the width is what used to be the length. This used to be this before I ended up cutting along my dotted line. Becomes this, becomes this. So the width is just the original height of my cylinder. So the width, I guess if I call the height of this cylinder capital H, then the width is just going to be equal to that capital H. speaking of which, I forgot to define this. This I'm going to call a small change in r delta r. I think you can see where this is going. That's going to turn into our differential. And then what about the length? The length, let me use a different color for it. How about purple? So the length is what used to be this. This, all the way around this circle. That, when you open it, turns into all of this, which turns into this, which turns into our length. And what was this before we unfurled it? If we treat the radius if we treat the inner radius and outer radius as being approximately the same, then we can just take whatever radius this particular shell had, whatever radius our shell we had. That's not even legible, is it? It says our shell, you're just going to have to trust me on that. If we take that radius, we can just use 2 pi r to calculate the circumference of this shell. And so that 2 pi r unwraps into this, then gets flattened into this, and ultimately gets flattened into this. So this length is equal to 2 pi r. So the volume of a shell, V of a shell, is equal to length, 2 pi r, times width, which is capital H, times the height, which is delta r. Okay. Now we can get the mass of a shell, because the mass of a shell is equal to the density times the volume of a shell. And when an object has uniform density, the density formula for a uniform object is simply the total mass over the total volume. The total mass, we'll just call it big M. I forgot to specify that. This cylinder has a total mass of big M and a maximum radius big R. So total mass, that's just a given. Total volume, we can write it as, let's see, density equals M over total volume for a cylinder would be pi r squared H. Pi r squared H. And so now we can get the mass of a shell. I guess I'll do it down here since I'm running out of space. Mass of a shell is equal to density, big M, over pi r squared H, times volume of a shell, which we just got, 2 pi r big H delta R. 2 pi r big H delta R. And here we see why the height, whoops, canceled the wrong thing. Whoops, no. The pi looks like an H. Sorry about that. And we see now from the H canceling out why the height does not factor into the moment of inertia formula for a cylinder that you see in most textbooks. So we're starting to see more and more of how we are supposed to get here. Come to think of it, actually, it was not such a bad thing that I crossed out the pi, because the pi also cancels out. Yeah, the pi cancels out with this pi over here. Okay, the day has been saved. So that's the mass of an individual shell, and I want to now put that into my moment of inertia for an individual shell, and then I want to sum those up. So the moment of inertia for the whole cylinder, the total moment of inertia is going to be the sum of the moments of inertia of a bunch of shells, is going to be the sum of, let's see, the mass of an individual shell is, we've got the 2 and the m and the little r, 2m little r over big R squared, and then delta R, that's all that's left out of that. So that's the mass of an individual shell, times R squared, and these R's are the same. They're just the radius of a particular shell. I guess we could call these Ri if we want to stay true to the summation notation. And we can just use our intuitive translation from sums to integrals. This is just going to become I total equals, if we make this an infinite sum, is going to be equal to the integral from, I guess we'd start at a radius of 0 to a radius of big R. Well, let me not get ahead of myself. We'll talk about the bounds in a minute. Let's copy over what we have. So we've got 2m over big R squared, and then we've got this R and this R squared. That's going to become R cubed, and then the delta R is going to become our dr. And then we're going to have our integration bounds. Since we're integrating with respect to R, we're going to go from R equals 0 to R equals big R. The radius of our, let me separate those so that they're easier to read. So the radii of our shells, we start with a shell of radius 0, so I guess an empty shell, and we move to shells of bigger and bigger radius until we hit the last shell at radius big R. That's the progression. That's how we are stacking our shells. Okay, the 2 and the big M and the big R squared, those are all constants that can be factored out. We would just be integrating R cubed dr, and that would be increase to 4 divide by 4. In fact, I don't even have to bother with factoring out. Let me switch colors and see if I can fit this down here. M over big R squared times R to the 4th all over 4, evaluated from 0 to big R. If I plug in 0, this is going to give me 0. And now that we've seen this, 3-4 times now, you might think when the bottom bound is 0 that you can just ignore it, but it really depends on what function you get. So don't be too quick to write off this step of the problem. There will be times where that 0 is actually going to give you something that matters. Anyway, 2m over r squared, or I guess over 4r squared I should say, times big R to the 4th minus 0 to the 4th. Okay, the 0 is gone, and then we've got 2 over 4 reduces to 1/2. Oh, the m just stays as is, and then r to the 4th over r squared is r squared. Would you look at that? Exactly what we were supposed to get. Okay, I think this might be a good place to leave things for now. I think the best thing to practice if you're a complete beginner, the best thing to practice would be kind of similar to what we did in the first example with dividing a cone into a bunch of disks. You can prove the volume formula for a pyramid. So that is a challenge that I think you can handle. See if you can come up with the volume formula for a pyramid. And it doesn't even matter what kind of pyramid it is. It doesn't matter if it's a square pyramid or a triangular pyramid or a hexagonal pyramid or whatever, but I would recommend that you just start with square pyramids. Those would probably be the easiest for you to deal with. So yeah, a challenge for you, challenge yourself, and see if you can prove to yourself using integration that the volume of a pyramid is 1/3 of the base times the height. 1/3 of the area of the base times the height. It should be quite similar to what I did with the cone. Maybe you can find a more streamlined process than me, because I'm not entirely happy with the way that I explained things today. I was even mentally rehearsing and everything all week, and I thought I had a very smooth way of explaining things, but yeah, I'm not entirely satisfied with this. I'm gonna think about this more and see if I can explain it better the next time I have to discuss this topic, which might be sooner than you think, because I feel like we might be able to use some more examples of this. But that remains to be seen. I most likely will be switching to a different topic next week. I don't know what that topic will be, but I wouldn't say I've entirely written this topic off quite yet. I feel like there's still a need to cover more things here. I just don't know what yet, and even if I did know what, I'm gonna need time to figure out how. This is the curse of intuition. When something is so intuitive to you that you kind of just did it without thinking about it and you don't know how to explain it. Well, I will worry about that on my own time. Hopefully, this has been helpful despite the admittedly confusing explanations. Hopefully you got something out of this just through sheer exposure to examples. Hopefully something clicked, but if things aren't quite clicking yet, I'll be reflecting on this and seeing if I can come back with a better way to go over all this stuff. Anyway, that's it for me. Take care, and I will see you in the next one.